Hello there, and welcome to Life Beyond Seen, where curiosity settles in softly beside you and science wanders at an unhurried pace. Tonight we're taking a slow journey into a world most people never think about, even though it has existed longer than any map, any city, or any bedtime story. It's a place hidden far beneath the coldest regions of our planet, a place where rivers flow without sunlight, where water moves through darkness under pressures most of us can't picture, and where the landscape is sealed off by ice thicker than skyscrapers are tall. These are the hidden rivers beneath the polar ice, and although we know they're there, reaching them, truly reaching them, is something that remains just out of our grasp. Before we wander into that quiet, frozen realm, I'd love to know something. Where are you listening from tonight? Are you wrapped under a blanket? Are you still finishing your day? Or maybe preparing to drift into sleep? Whatever your moment looks like, it's a gentle thought to imagine you and I sharing this small stretch of time together, while somewhere on Earth, far north or far south, ice older than human civilization presses down on silent currents flowing in the dark. If you find comfort in these slow explorations, or if you simply enjoy ending your day with a side of wonder, I'd be grateful if you gave this video a like, or subscribed, or perhaps shared it with someone who could use a bit of calm. It helps this quiet corner grow and lets others find the same peaceful pause you're settling into right now. So take a breath, let your thoughts slow down a little, and let's begin. There's no rush. These hidden rivers have been waiting for thousands of years, and they'll still be there long after we finish this story. What makes them so mysterious isn't just that they're out of sight, it's that they exist in conditions that seem almost contradictory. Water under ice should freeze, especially under ice that is impossibly thick. Yet somehow these rivers keep moving. They carve channels, feed hidden lakes, and influence the world above them in ways we're only beginning to understand. The more we learn, the more it becomes clear that these rivers are not simply trapped features of a frozen world. They're active, dynamic systems that hold clues about climate, geology, life, and Earth's deep history. But they are also out of reach, protected by miles of ice so cold and so heavy that they shut out nearly all attempts to descend through them. To understand why we can't reach these rivers, it helps to know first just how layered and stubborn the landscape above them is. The ice sheets covering Antarctica and Greenland aren't like frozen ponds or winter lakes. They're entire continents of ice, built up snowflake by snowflake year after year, until the weight of all that frozen mass presses downward with astonishing force. At the thickest points, the ice can reach more than 3 kilometers deep. When you think about that depth, consider that it's equivalent to stacking the tallest buildings on Earth on top of each other. And at the bottom of that unimaginable stack lies water, flowing in narrow, dark channels. These rivers do not sit still. They move beneath ice that weighs down on them with millions of tons of pressure. They shift as the ice above them flows. They swell and drain and sometimes vanish into the unseen bedrock below. They're not quiet or frozen in time. They live in their own strange rhythm, responding to forces too huge to fit comfortably in our everyday imagination. And yet, for all that movement, they remain separated from us by conditions that are far from welcoming. Getting to them isn't simply a matter of drilling straight down. The ice itself behaves more like a slow-moving ocean than a solid surface. It flows, it bends, it fractures unpredictably. Temperatures fluctuate in ways that make equipment malfunction. Even the act of drilling can change the environment being studied. Heat introduced by the machinery can alter the ice, contaminate the water, or close the borehole as fast as it opens. Every attempt to reach those hidden places must be planned with almost surgical precision, and even then, success is never guaranteed. But that's just part of the challenge. Another lies in the sheer remoteness of these regions. The poles are some of the harshest places on Earth to work. Imagine trying to build a scientific base on a surface that never stops shifting, in temperatures that can snap metal, with winds strong enough to erase footprints in seconds. Every shipment of equipment, every gallon of fuel, Every piece of insulation must be brought in at enormous cost, often only during a narrow window of favourable weather that might last a few weeks. And once researchers are there, they're surrounded by conditions that demand constant attention. The cold can empty batteries faster than they can be charged. The isolation means that if something breaks, you fix it yourself with whatever you have. And the ice beneath your feet is not stable. It flows, it cracks, it hides crevasses deep enough to swallow entire vehicles. For most of human history, we didn't even know these rivers existed. We thought the ice sheet sat directly on bedrock, perhaps cold and unmoving. But as technology improved, especially radar systems capable of penetrating ice, new pictures began to emerge. They revealed lakes, channels, basins and branching waterways running like veins across a world no one had ever seen. Some of these rivers stretch for hundreds of kilometres. Some drain into hidden lakes beneath the surface. Others disappear into the deep pathways carved by the slow scraping motion of glaciers. Their existence reshaped how scientists understand the entire polar system, but seeing them from above is not the same as touching them, sampling them, or exploring them directly. That's where the real difficulty begins. Water beneath the ice is heavily pressurized, close to freezing but still flowing. If a drill pierces a pocket of this water, the sudden release of pressure can cause the borehole to collapse or explode outward. If a drill warms the surrounding ice too much, the meltwater freezes again around the machinery, trapping it permanently. If equipment is lowered into the water, the extreme cold can cause electronics to fail in minutes. And even if all that is solved, there's another essential issue to consider: contamination. These hidden environments have been sealed off for millions of years. Introducing modern microbes, chemicals, or even microscopic debris could irreversibly change them. So any attempt to reach these rivers must be almost impossibly clean. Tools must be sterilized carefully, sometimes with methods more rigorous than those used in spacecraft assembly. Even when teams spend years planning for every variable, the ice has a way of reminding us that it's not easily persuaded. Boreholes can refreeze, equipment can be lost, water pressure can surge unpredictably. Each attempt to reach these rivers, even with modern technology, is a slow and uncertain process, and the margin for error is small. There are times when scientists make the long journey to a drilling site, prepare everything, wait for weather windows, and then return home without ever making it to the water they hope to study. For now, we rely heavily on remote sensing to map the networks beneath the ice. Radar helps us see shapes and boundaries. Satellite measurements reveal how the ice above moves in response to the water below. Seismic studies send vibrations through the ice to detect hidden features. All of these techniques offer clues, but none of them deliver the same understanding as direct exploration. They give us outlines and shadows, hints and suggestions. Enough to know these rivers exist and enough to know they matter, but not enough to fully understand them. And that's where the story begins to unfold. These rivers aren't just isolated curiosities trapped beneath the ice. They affect how glaciers slide, how ice sheets lose mass, and how sea levels rise. They influence the stability of entire regions. They might contain ecosystems that evolved in complete isolation for millions of years. They may hold clues about how life could survive on worlds like Europa or Enceladus, moons that seem to have oceans buried beneath ice even thicker than Earth's. They are more than just hidden waterways. They are windows into Earth's past and future, and perhaps even the nature of a life elsewhere. Yet for all their importance, the truth remains the same. We can't reach them easily. We stand above them, aware but distant, using the best tools we have while knowing there's so much more waiting below. The distance might only be a few kilometres downward, but in terms of access, it's still worlds away. Still, the effort continues. New technologies are being designed. Autonomous probes that can travel through ice without overheating. Drills that can stay sterile in unforgiving conditions. Sensors that can survive extreme cold and crushing pressure. Step by step, the barrier between us and those hidden rivers gets thinner. For now, though, As we begin this long exploration tonight, all we can do is look down in imagination and consider the strange, dim world waiting beneath the ice. A world shaped by pressure and darkness, untouched by human hands, moving in its own slow way beneath a frozen realm that keeps it sealed from view. And as we start to follow that path more closely, there's something surprisingly soothing about how distant it still is, like a secret kept by the planet itself. This is where our journey begins, near the surface but just on the edge of a world we're only beginning to uncover, a place where the first hints of cold, depth, and hidden movement are waiting to be traced deeper and deeper into the frozen ground. From here, the story simply continues forward, moving gently toward the vast and stubborn landscape that sits above those rivers, the frozen roof of the world that shields everything below it from sight. Just let your thoughts settle as we drift into that part of the story next. The ice above these rivers is its own strange world, and understanding it brings us closer to the hidden flow beneath it. When you start to picture the immense expanse of polar ice, it's easy to imagine a simple frozen sheet stretching across a landscape, something flat, white, and uncomplicated. But the ice covering the poles is nothing like the thin layers most of us have walked across in winter. It isn't quiet in the way we expect, and it isn't still in the way we might assume. Instead, it's more like a slow, heavy ocean, made not of water, but of frozen layers stacked so deeply that the scale of it becomes difficult to take in at first. This frozen mass forms a kind of roof over the hidden world below, and everything happening under it is shaped by the weight, the cold, and the movement of that enormous body of ice. Even if you've seen photographs or documentaries showing endless white fields, they only hint at what's really there. The ice sheets of Antarctica and Greenland aren't surfaces you can casually walk across without thinking. They're environments built over millions of years as snow settled, compressed, and transformed into dense ice. Every snowfall that doesn't melt becomes part of a layer. Year after year, century after century, layer upon layer builds up until the oldest ice at the bottom is so compacted that it carries the imprint of climates that no humans ever witnessed. Trapped bubbles of ancient air, preserved crystals, tiny bits of dust from long-gone volcanic eruptions, even microscopic traces of past ecosystems. Thousands of years of Earth's history compressed under unimaginable pressure. With every added layer, the weight above increases. Ice that seems too solid to move under normal circumstances begins to deform under that pressure. It flows outward and downward, reshaping itself constantly, even if the movement is too slow for a casual observer to detect. The entire sheet, kilometers thick, is always on the move. Some sections push toward the coast, others sink into deeper basins, and the deepest parts are drawn toward areas where the bedrock dips or tilts. The ice flows, stretches, twists, and compresses in ways that change from year to year and century to century. Because of that movement, the surface can be full of hidden dangers. Crevasses form where the ice is pulled apart, some narrow and others wide enough to swallow whole vehicles. They might stretch for hundreds of meters, their icy blue walls disappearing into darkness. You can walk across a nearly flat surface unaware that only a few steps away lies a crack so deep you can't see the bottom. These fractures shift as the glacier moves. They open, close, change shape, or get buried beneath fresh snow. Anyone working on the ice must move with caution. Ropes, harnesses, teams staying connected so no one disappears suddenly into a void. Even where the surface appears stable, it's never still. Snowstorms can arrive with little warning, swallowing camps in drifts as fast as they can be cleared. Winds carve patterns into the snow until it looks more like carved stone than something soft. Temperatures drop low enough to freeze metal, crack plastic, and make breath turn instantly into tiny crystals. The air itself feels thinner and drier. Voices sound different. Machinery behaves unpredictably. Simple tasks become slow and careful. Every motion requires layers of clothing that turn bending or lifting into stiff, clumsy movements. Beneath the surface, the ice grows denser with depth. its texture changes. Near the top, it's firm but still structured like compacted snow. Farther down, it transforms into something more like solid rock, smooth and compressed, clear in places and clouded in others. The deeper it goes, the more it behaves like a heavy, viscous material that shifts gradually under its own weight. When scientists drill through it for research, the extracted cylinders show this transformation clearly. Upper layers appear white and grainy. Middle layers are more compact and bluish. Lower layers are dense, almost glassy, with trapped air bubbles reduced to faint lines or dissolved entirely. Each metre of depth represents a jump backward in time, and yet these layers are constantly flowing downward and outward in response to pressure. The top of the ice sheet is shaped by the climate above it. Snowfall adds mass. Wind redistributes it. Sunlight may create shallow melt ponds in certain regions during the short summer months. But these features rarely reach deep because most of the surface remains far below freezing throughout the year. Even the sunniest days can't penetrate more than a thin surface layer. The deeper parts of the ice stay cold with a consistency that is almost absolute. Temperatures a few meters below the surface remain locked in near permanence, indifferent to whatever season exists above. This roof of ice also has its own internal plumbing. Meltwater generated at the surface can sometimes disappear into cracks, flowing downward along channels until it refreezes. When enough water gathers, it can lubricate the ice sheet's base, helping it slide more easily. Sometimes the water doesn't reach the bottom at all, and instead becomes trapped midway, creating pockets that shift pressure around them. Even when the surface looks calm, there are rivers and tunnels of meltwater forming and refreezing above the deeper layers. These pathways shift constantly, depending on temperature, storm patterns, and the terrain hidden underneath. As temperatures rise around the world, the dynamics of this frozen roof begin to change faster than they did in the past. Surface melt increases in some regions, creating more water that tries to find its way downward through cracks. Ice shelves, floating extensions of the continental ice, fracture more easily when water works its way into surface crevasses and forces them wider. The flow rates of glaciers accelerate in some places. In others, the balance shifts and new surface patterns appear as the ice tries to adjust to changing conditions. The roof is not static. It is continually reshaped by climate, by gravity, by the internal pressure of its own mass. The size of the ice sheets is one of the central reasons the hidden rivers below remain out of reach. Drilling through thin ice is straightforward by comparison. The thickest parts of the Antarctic ice sheet exceed 3 kilometers. That depth is greater than some mountain ranges at all. Drilling equipment must remain functional throughout the entire descent. Fuel must be transported across long distances to power the machinery. Teams must maintain the drilling operation for weeks or months in conditions where even keeping warm is a full-time challenge. And all of this must happen while ensuring the hole doesn't collapse, freeze shut, or contaminate what lies beneath. At such depths, ice behaves in ways that challenge engineering assumptions. The pressure from above causes the walls of any drilled path to creep inward. Even when hot water drilling is used, where a jet of heated water melts a hole downward, the surrounding ice begins refreezing almost immediately once the drill is withdrawn. Keeping the borehole open requires constant circulation of warm water. If the system stops, even briefly, the passage begins to seal. Imagine trying to hold a tunnel open in something that wants nothing more than to close around it. That's the kind of environment researchers face. Temperature differences within the ice sheet also create gradients that affect drilling. Near the bottom, the temperature increases slightly due to geothermal heat from Earth's interior. Even a few degrees of warmth can change how ice behaves. Pressure melts and refreezes ice at different points, creating variations in hardness. These subtle shifts require adjustments in drilling technique. A method that works well 1,000 meters down might fail at 3,000 meters. Sensors must constantly monitor conditions. Engineers must adapt equipment on the spot. And all the while, the ice continues to move, slowly but steadily, sometimes altering alignment by centimeters or more, While all these physical challenges exist, the logistics create their own set of barriers. Transporting equipment to drilling sites often requires specialized aircraft, capable of landing on snow and ice runways. Fuel must be stored in insulated containers to prevent gelling. Teams must build shelters that can withstand storms strong enough to bury buildings. Heating, power generation, food storage, and communication systems must function reliably for long stretches without external support. Even something as simple as washing equipment requires careful planning, since water sources are frozen and must be heated before they can be used. Every step must be accounted for because mistakes can be costly in time, resources, and safety. These demanding conditions explain why reaching the bottom of the ice sheet is something only a handful of teams have ever attempted. Even the most advanced operations measure their progress by meters per hour. And once they reach a point close to where the hidden rivers flow, the challenges only grow. The last stretch of ice, where pressure is highest and temperatures are most stable, is also where the risk of contamination becomes most serious. Any microbe that sneaks into the system, any tiny chemical from drilling equipment, or any accidental change to the environment below could alter the water's composition in ways that erase the very information scientists want to study. Despite all these barriers, the frozen roof of the world remains compelling. It is the entry point to a hidden landscape that has persisted beyond the reach of sunlight for millions of years. Even without touching the rivers below, studying the ice itself reveals patterns and clues about the forces shaping the land beneath it. The flow of the ice can be traced from satellite observations. The slight variations on the surface reveal where the bedrock underneath dips into valleys or rises into ridges. Subtle changes in elevation over time show where water might be accumulating or draining below the surface. Every whisper of movement on the surface hints at something happening deep underneath. The ice acts as a lid, a shield, a barrier, and a conveyor all at once. It prevents heat from escaping too rapidly from the earth below. It redistributes its own weight over time, moulding itself to the terrain beneath it. It adds pressure to the rocks and sediments at the bottom, creating conditions that would not exist in any other environment on the planet. All these forces play a role in shaping the hidden rivers. The ice pushes down, the water moves around obstacles, and the entire system adjusts in slow, powerful motions that continue day and night. By understanding this frozen roof, scientists hope to gain insight into how the rivers form, how they change, and how they affect the movement of the ice above them. The way the ice flows is tied directly to the water beneath it. In some areas, water acts as a lubricant, allowing glaciers to slide more easily. In others, lakes form and drain in cycles that alter the speed of the ice sheet. These interactions affect how quickly ice reaches the ocean and how much water enters the global seas. So while the rivers themselves are hidden, the ice roof above them provides a rich set of clues that researchers can study to build a clearer picture of the entire system. The ice sheet is not just an obstacle, it is also an integral part of the story. Without it, the hidden rivers would not exist in their current form. Without the weight pressing down, there would be no pressure-melted water at the base. Without the constant movement, there would be no channel networks reshaped by flow. Without the insulating layer, the cold would freeze everything solid. The ice and the water are bound together in a relationship that defines both. As we continue this journey downward, imagining what lies beneath the layers, the frozen roof becomes a necessary part of the path. It's the boundary between what we can study firsthand and what remains inaccessible for now. And through understanding this boundary, we get one step closer to the strange and active world that lies below it, where rivers run in complete darkness under pressure that would crush most equipment in moments. From here, the story moves steadily toward those unseen currents themselves, to explore what flows under all that weight, how it stays liquid, and why it continues to move through depths that seem too cold and too ancient to allow such things. The world beneath the vast polar ice sheets is unlike anything on the surface. Once you move past the heavy layers of compressed snow, the creaking ice, and the shifting fractures above, you reach a depth where sunlight has never entered, not even in the faintest, most diluted form. It's a place where darkness isn't just the absence of light, but a constant, unchanging state. The hidden rivers that move through this deep region exist entirely without illumination. They don't glint, shimmer, or sparkle the way rivers on the surface do. Nothing in their environment reflects anything because there is nothing to reflect. Yet these rivers are moving, active, and surprisingly complex despite being sealed beneath thousands of meters of ice. When most people imagine water trapped under such extreme cold, the instinctive assumption is that it should be frozen solid. After all, this is the base of ice sheets that hold temperatures far below anything the warmest summer day could overcome. But the deeper you go beneath those layers, the more surprising the environment becomes. Instead of a solid bed of ice resting on rock, many regions hold channels where water flows in networks across the landscape. These rivers snake their way along valleys, around ridges, and through basins that have existed longer than any known civilization. They form pathways that drain meltwater from the bottom of the ice sheet, collecting into lakes or dispersing across sediment, reshaping the land beneath in ways that no one can see directly. Although these rivers are described as flowing doesn't always mean what it does on the surface. Some of these waterways move slowly, creeping along in thin films only millimeters thick. Others move more like conventional rivers, with speeds influenced by the shape of the bedrock, the slope of the terrain, and the amount of meltwater feeding them. A few may surge when pressure builds behind natural barriers, releasing their stored water in sudden bursts. These changes can cause the ice above to shift, rise slightly, or sink, providing one of the few indirect clues that something dynamic is happening far below. To understand why these rivers exist at all, it helps to consider the environment at the bottom of the ice sheet. The pressure here is immense. Every layer of snow that has fallen over tens of thousands of years adds weight to the layers below. By the time this weight reaches the base, it becomes strong enough to press the ice into a state that lowers its melting point. Under standard conditions, water freezes at 0 degrees Celsius, but under extreme pressure, that threshold drops. Ice that should be solid begins to turn into water because the pressure forces the molecules into a different arrangement. This pressure melting is one of the key reasons hidden rivers can continue to flow. Even if the surrounding ice is well below freezing, the very fact that it is weighed down so heavily allows some of it to melt. Geothermal heat from the Earth's crust also plays a role. Even though the heat from the planet's interior is faint, it's enough to raise the temperature at the base of the ice sheet by a few degrees, which can be the difference between solid ice and liquid water in a high-pressure environment. These two forces, pressure and geothermal heating, create pockets where water forms, gathers, and eventually begins to move. Once water begins to flow, it shapes the bedrock below. It carves small channels that widen over time. It picks up sediments, minerals, and tiny particles that help deepen the pathway. The water may flow along smooth rock surfaces or weave through thick layers of sediment left behind from past geological eras. These rivers can connect to larger lakes, some of which span dozens of kilometers. They can feed networks that extend across entire regions beneath the ice. The environment becomes a kind of hidden drainage system that responds to cycles of melting, freezing, and shifting as the ice sheet moves above it. However, the darkness in which these rivers exist is not simply a lack of light. It defines how everything happens there. Without sunlight, there is no direct source of heat, energy, or photosynthesis. The temperatures remain consistently cold, hovering near the melting point but rarely rising above it. The water moves quietly, shaped mainly by forces from the ice above and the rock below. There is no surface weather, no storms, no seasonal fluctuations beyond what percolates through from above. The conditions remain steady through long stretches of time, changing only when the larger ice sheet shifts or when geological heat fluctuates. It's easy to imagine such an environment as barren, completely empty, and devoid of anything interesting beyond cold water and cold rock. but scientists have good reasons to believe these rivers may contain far more than just water. Even though they are cut off from the surface world, they might hold sediments, organic material, and even microbial life that adapted to survive without sunlight. These organisms, if they exist, would rely on chemical energy rather than light, drawing sustenance from minerals in the bedrock or from compounds carried by the meltwater. Such ecosystems, if confirmed, would challenge assumptions about where life can survive on Earth, and they would provide important clues about how life might develop on icy worlds elsewhere in the solar system. But even without considering life, the physical movement of these rivers has a significant role in the dynamics of the ice sheet above. Water acts as a lubricant. When enough of it gathers in certain regions, it can reduce friction between the ice and the bedrock, allowing the ice sheet to slide more easily. This can accelerate glacier movement toward the ocean. In some cases, it can cause sudden shifts in flow that are noticeable from satellites. When a hidden river drains a subglacial lake, the ice above might sink by a meter or more as the support beneath it changes. These shifts offer one of the few opportunities researchers have to track the behaviour of the unseen rivers below, serving almost like ripples on a surface that reveal what's happening underneath. Although the existence of these rivers is now well accepted, the details of how they behave remain uncertain. Every river system beneath the ice is shaped by unique factors: the topography of the bedrock, the thickness of the ice above, the amount of geothermal heat, and the history of the region's climate. Some rivers may remain stable for millennia, while others may shift their paths more frequently. The pathways aren't fixed the way rivers on the surface often are. The movement of the ice itself may carve new channels or block old ones. A shift in surface conditions, such as increased melting due to warmer temperatures, can add more water that eventually finds its way to these deep layers, altering the flow and pressure patterns. The sediments carried by these rivers also reveal information about Earth's past. If researchers could sample the water directly, they might find minerals that formed before the ice sheet existed. They might uncover patterns that show how long certain regions have been frozen, or how the ice sheet responded to past climate changes. Some sediments could hold traces of ancient vegetation or organic material that was buried long before the ice formed. These clues could help scientists understand not just the present-day behaviour of the ice sheet, but the geological and environmental history of the continent beneath it. Of course, accessing that information is the challenge. The rivers exist in a zone that is extremely difficult to reach. Even if scientists were able to drill all the way to the bottom, they would need to sample the water in a way that doesn't introduce modern contamination. Once the drill enters the water layer, the pressure may force the water upward, potentially altering the environment being studied. Equipment lowered into the river may freeze, malfunction, or become trapped. And even if a sample is successfully retrieved, it must be stored carefully to preserve its chemical structure and biological integrity. These obstacles mean that while scientists know much more about the rivers than they did a few decades ago, direct evidence remains limited. This limited direct evidence has led researchers to rely on indirect methods to understand these hidden systems. Radar instruments can help map where the ice base is smooth, suggesting flowing water, versus where it is rough, suggesting frozen conditions. Satellite observations reveal changes in ice elevation that correspond to the filling and draining of subglacial lakes. Seismic studies measure how vibrations travel through the ice and bedrock, offering clues about liquid versus solid zones. All these tools together create a picture of the rivers that is detailed enough to show their broad outlines but incomplete when it comes to finer details. The more scientists study these hidden rivers, the clearer it becomes that they are part of a much larger network. Instead of isolated features, they form an interconnected system that spans entire regions beneath the ice sheet. Water may travel long distances, passing through multiple basins, feeding into large lakes, and then continuing onward. Some of the largest subglacial lakes, such as Lake Vostok in Antarctica, hold enough water to rival major surface lakes. The rivers feeding and draining these lakes play a role in maintaining their levels and shaping their environments. The entire system acts like a hidden watershed, except one that remains locked in permanent cold and complete darkness. Because of their importance, researchers continue to refine their understanding of how these rivers form, how they persist, and how they influence the ice above. Improved models incorporate more variables, such as changes in ocean temperature that affect coastal regions of the ice sheet, or shifts in atmospheric patterns that alter snowfall. As the climate warms, some regions may see more surface melt that seeps downward. This could add more water to the hidden drainage system, potentially accelerating the flow of ice toward the ocean. Understanding how the rivers respond to changes in their environment is essential for predicting future sea level rise and anticipating how ice sheets will evolve. Despite relying heavily on models, satellite data, and remote sensing, the fact remains that these rivers remain physically untouched by most scientific instruments. They exist in a domain where the challenges of access create a barrier that is as much technological as it is environmental. Every attempt to reach them must contend with cold temperatures, shifting ice, limited resources, and the need to maintain sterility. Even the idea of sending autonomous probes into these rivers faces logistical hurdles. The probe would need to melt its way through thick ice without refreezing, survive the intense pressure, navigate channels it cannot see, and return data through kilometers of ice. Each step introduces complications that current technology is only beginning to address. Still, the existence of these rivers shapes the entire polar landscape. They influence how glaciers move, they control the distribution of pressure beneath the ice sheet. They respond to shifts in climate. They store and transport heat and sediments in ways that affect the long-term evolution of the region. And even though no one has seen them directly, their presence is undeniable. They are as much a part of the polar environment as the ice above and the rock below. Imagining these rivers moving in constant darkness, under pressure that would crush most objects, creates a sense of how different this hidden world is from the one we know. The rivers don't behave according to the same rules that shape rivers on the surface. They don't experience day or night. They don't freeze in winter or thaw in summer. They aren't fed by rainstorms or snowmelt in the way familiar rivers are. Their rhythm comes from the ice itself, from the slow melting caused by weight and geothermal warmth, and from the pressures that push them forward. As we continue moving deeper into this exploration, the next natural step is understanding how water in such conditions manages to stay liquid at all, how it survives in an environment where nearly everything suggests it should be frozen. The forces that make these rivers possible are as important as the rivers themselves, shaping every aspect of how water exists in this hidden world beneath the polar ice. When you think about the conditions beneath the polar ice, the first instinct is to imagine a world so cold that nothing could possibly stay liquid for long. After all, the temperatures recorded on the surface of Antarctica are some of the lowest on Earth, and even in regions that see a bit of summer sunlight, the warmth rarely reaches deep enough to change what happens at the bottom layers of the ice sheet. Yet the water beneath all those layers doesn't freeze into one solid mass. Instead, it survives in a place where logic says it shouldn't. It moves, it collects, it drains, and it sustains systems that behave more like underground plumbing than static frozen rock. Understanding how this water stays liquid is central to understanding why these hidden rivers exist at all, and why they continue flowing in environments that appear completely incompatible with liquid water. The conditions at the base of the ice sheet look frozen from above, but that impression only reflects what happens near the surface. The deeper you go, the more surprising the environment becomes. It is not cold in the absolute way people imagine. Instead, it is a place where pressure and heat combine to create an unusual balance. Ice near the bottom is pressed so tightly by the weight above that the rules we associate with freezing water begin to shift. Under normal atmospheric pressure, you can confidently expect water to freeze at 0 degrees Celsius, but change the pressure significantly and that threshold moves. Compress the ice with millions of tons of weight, and the point at which water freezes drops low enough to keep some of it in a liquid state, even though the temperatures remain below 0. This effect is called pressure melting, and it is not just a theoretical concept. It is a practical, observable phenomenon that plays a significant role in glacial movement worldwide. You can see a smaller version of it when ice skaters glide across a rink. The blades of the skates press down with enough force to momentarily melt a thin film of water beneath them, allowing the skater to slide. Under the polar ice sheets, this same idea occurs on a massive scale. The pressure from kilometres of ice creates a zone at the bottom, where melting can occur naturally, even in the absence of sunlight or external heat. The temperature of the ice remains below freezing, but because the pressure is so intense, the ice at the base begins to melt anyway. The melt that forms at this depth gathers into thin layers. Some of it forms films that lubricate the interface between the ice and the bedrock. Some of it collects in depressions created by uneven terrain, and some of it begins travelling along pathways that ultimately become the hidden rivers flowing in darkness. This water doesn't form because the environment is warm. It forms because the ice above exerts a force strong enough to push it past the typical limits of freezing. The environment does not care much about what seems logical on the surface. It operates according to the physics at the depth where the water exists. Geothermal energy adds another crucial factor. Even though geothermal heat is generally weak compared to surface heat sources, it rises steadily from the Earth's interior. Rock absorbs heat slowly and holds it well. When that warmth meets the base of the ice sheet, it transfers upward, bringing the temperature closer to the melting point. Even a change of 1 or 2 degrees can influence the balance between solid ice and liquid water. Because the ice above is so thick, the heat doesn't dissipate easily. Instead, it creates small pockets where melting persists with surprising stability. Over time, these pockets connect, forming channels and pathways that contribute to the hidden drainage system beneath the ice. This geothermal effect varies depending on the underlying rock structure. Some regions have slightly higher geothermal activity than others due to differences in crust thickness or the presence of faults. These warmer areas are more likely to host active rivers or larger subglacial lakes. In places where the geothermal flow is somewhat weaker, the water may form more slowly, but the pressure melting still ensures that some liquid remains. Together, pressure and geothermal heat maintain an environment where water can exist without freezing into solid ice, even though it is surrounded by one of the coldest regions on the planet. The terrain beneath the ice plays just as significant a role in the survival of this water. The bedrock is far from smooth. It includes valleys carved by ancient glaciers, ridges left behind by mountains long eroded, basins formed by tectonic movements, and broad plains covered with layers of sediment deposited before the first ice sheets formed. The water that melts at the base flows into these features. It collects in the low points and finds pathways along sloped surfaces. The roughness of the terrain creates natural channels that guide the direction and speed of the water. Where the bedrock dips deeply, larger lakes may form. Where it rises sharply, the water may pool or get forced into narrower channels. The landscape under the ice is as influential as the ice above when it comes to determining how the water moves. Another important factor is the insulation provided by the ice itself. While the ice appears cold and exposed on the surface, its mass acts as a thermal buffer. It insulates the base from the extreme temperature swings happening above. Even when surface temperatures drop dramatically, that cold doesn't reach the bottom layers easily. The base remains more stable, affected mostly by the geothermal heat from below rather than the seasonal temperature changes above. This stability helps maintain conditions favourable to liquid water. It means the water doesn't freeze instantly even when the surface experiences intense cold. The movement of the ice sheet also contributes to the presence of liquid water. Ice constantly flows under its own weight, slowly shifting across the landscape. This movement generates friction between the ice and the bedrock. Although the friction is low in absolute terms, the enormous scale of the ice sheet means the cumulative effect can generate additional heat. This friction adds yet another source of warmth that helps the water stay liquid. Combined with the insulation from the ice and the geothermal heat from below, the friction ensures that the temperature at the base remains high enough to avoid complete freezing. The water itself influences its ability to stay liquid. As it moves, it transports heat from regions of higher geothermal activity to areas that would otherwise be too cold to maintain a liquid state. This redistribution helps maintain flow across a wide area. The water may be near the freezing point, but because it is constantly moving, it avoids remaining stationary long enough to solidify entirely. Water flowing across rock, even slowly, resists freezing more effectively than water that sits still. All these factors contribute to an unusual but stable environment where water can survive despite conditions that seem too cold for it. The rivers flowing in this hidden world do not behave like surface rivers. They do not react to sunlight or rainfall. They do not freeze in winter or swell in spring. They move according to the physics of pressure and geology, not weather patterns. Their existence depends on forces that persist regardless of what happens on the surface. The characteristics of the water itself reveal more about the environment. Subglacial water is often rich in minerals due to constant contact with the bedrock. As it flows across sediments and rocks, it dissolves chemical compounds that would otherwise remain trapped. These minerals can contribute to chemical reactions that release small amounts of additional heat. In certain conditions, microbial life might use these minerals as a source of energy. If such life exists, its metabolic activity could contribute a tiny amount of heat as well. This biological contribution would be minimal, but in an environment where every bit of warmth matters, even small effect can help maintain the liquid state. Salinity also influences how water behaves under the ice, though in most subglacial systems the water is not particularly salty. However, in coastal regions or areas where older sediments have high salt content, the water may carry enough dissolved minerals to lower its freezing point slightly. This allows it to remain liquid under conditions where pure water would freeze. The presence of salt is not the primary factor in keeping these rivers from freezing, but it can contribute in specific locations. The pressure from above does not remain constant across the entire ice sheet. It varies depending on the thickness of the ice and the weight distribution across the region. Variations in pressure cause variations in the melting point. As the ice moves and the landscape shifts beneath it, the pressure changes subtly. These shifts can open new channels, close others, or alter the direction of existing rivers. Water follows the path of least resistance, and the ever-changing pressure landscape ensures that the pathways evolve gradually over time. The environment remains dynamic even though the changes might take years or centuries to become noticeable at the surface. One of the paradoxes of this hidden world is that it remains incredibly sensitive to changes above it, despite being physically isolated. Small changes in surface temperature can influence the amount of meltwater that seeps downward through cracks and crevasses. When this meltwater reaches the bottom, it adds volume to the existing rivers and lakes. Even if only a small percentage of surface melt reaches the base, the effect accumulates. This additional water can increase flow rates, alter pressure balances, and create new channels over time. The system responds to these changes slowly but steadily, reflecting the connection between surface climate and the hidden environment below. The insulation provided by the ice is also vulnerable to long-term changes. As the ice thins in some regions due to melting at the margins or increased surface melt, the insulation decreases slightly. This can affect the geothermal balance at the base. If the ice thins enough, the pressure melting effect weakens. The temperature at the base may shift toward freezing more easily. These subtle changes can influence whether water remains liquid or freezes in certain pockets. Over long periods, such shifts could reshape the drainage system beneath the ice entirely. Despite the complexity of these processes, the water beneath the polar ice remains surprisingly stable. It is not in danger of freezing solid anytime soon. The combination of pressure, geothermal heat, insulation, and motion creates conditions that have kept these rivers flowing for thousands of years. They survived fluctuations in climate, variations in ice thickness, and changes in geological activity over vast periods. The environment might shift gradually, but the forces that maintain liquid water at the base of the ice sheet are strong and persistent. Understanding how this water survives where it shouldn't is essential to understanding the broader dynamics of the polar regions. The rivers influence the movement of the ice sheet, the stability of the glaciers, and the long-term patterns of sea level change. They shape the bedrock beneath them through erosion and sediment transport. They may even influence the chemistry and biology of the hidden ecosystems below. Their persistence is a reminder that even in the coldest, darkest places on Earth, the laws of physics and the structure of the planet create pockets of unexpected activity. As we continue exploring this environment, the next step naturally involves looking at how the immense weight of the ice sheet shapes everything happening at the bottom. The pressure from above is not just a factor in keeping the water liquid. It also determines how the water moves, how the bedrock deforms, and how the entire system evolves over time. Understanding that weight brings the story closer to the deeper forces shaping this hidden world beneath the polar ice. When you picture an entire continent covered in ice, it might be tempting to imagine something delicate or fragile simply because ice feels delicate in everyday life. A thin sheet on a pond, frost on a window, the layer that cracks when you step on a frozen puddle. But the ice sitting over the hidden rivers at the poles is nothing like that. It is not fragile. It is not thin. It is not temporary. Instead, it is a massive, towering body that weighs more than almost anything else found in nature. And that weight changes everything happening beneath it. The pressure exerted by this ice is so intense that it shapes the bedrock itself. It presses down on valleys that were carved long before the ice formed. It bends the crust of the earth over time. It influences how water moves and where it collects. It creates environments that would be impossible under ordinary circumstances. To understand why the hidden rivers flow the way they do, why they stay liquid, why they change shape, and why they remain so difficult to reach, you have to understand the immense force created by the weight of this frozen mass above them. This weight isn't uniform across the entire landscape. The ice sheets vary in thickness depending on snowfall, climate patterns, and the topography beneath them. In some regions, the ice is over 3 kilometers thick. In others, it thins as it approaches the coast, forming floating shelves where the ice begins to meet the ocean. But no matter where you look, the pressure at the bottom of these sheets is staggering. Every additional layer of snow compresses the layers below. Eventually, this compaction creates a dense, heavy material that behaves differently from ordinary ice. Its density increases until it approaches the weight of solid rock. When this mass settles into place, it transmits its force downward into everything beneath it. To understand the scale of this pressure, imagine placing a skyscraper on top of a single square meter of ground. Now imagine stacking several skyscrapers on that same spot. The pressure from the ice sheet is even greater than that in many places. It presses downward with a force that constantly reshapes the land beneath it. Over long periods, it can cause depressions in the bedrock where the crust slowly bends under the weight. These depressions can reach hundreds of meters deep, altering the flow of water and the patterns of movement beneath the surface. This downward force also affects the ice itself. As the weight builds, the ice becomes more flexible, not in the way rubber bends, but in the way extremely slow, dense materials deform over long periods. Ice under such pressure doesn't stay rigid. It behaves like a very slow-moving, thick fluid. The ice flows outward from the centre of the sheet toward the edges, driven by gravity. This movement resembles the flow of honey, except on a scale that spans hundreds of kilometres and moves so slowly that you could watch it for an hour without noticing any change. Over years and decades, however, the movement becomes undeniable. The ice stretches, compresses, shears, and slides in response to the forces acting on it. This constant motion means the pressure at the base is never completely stable. As the ice flows, it drags its weight across the landscape, redistributing the force on different areas of the bedrock. In some places, the ice presses harder, increasing the melting point shift. In others, the pressure eases slightly, allowing areas to refreeze. This dynamic balance helps determine where water can persist and how it moves. The hidden rivers respond to these gradual shifts by adjusting their pathways, either carving deeper channels or finding new routes through the sediment and rock. The weight also affects how heat moves through the system. The ice acts as a massive insulator, trapping geothermal heat rising from the Earth's crust. This heat would normally dissipate more quickly if not for the insulating effect of the thick ice. But because the heat remains trapped, it contributes to melting at the base. The pressure ensures that the melting point is lower than it would be on the surface, so even small amounts of geothermal warmth become significant. The combination of insulation and pressure creates a delicate but persistent environment where liquid water can remain stable despite the cold above. This stability does not mean the environment is uniform. In fact, the variations in thickness and weight across the ice sheet create a patchwork of conditions at the base. Some areas experience constant pressure melting, maintaining continuous water flow. Others may freeze intermittently as the balance shifts. The hidden rivers are not straight channels carved long ago and preserved unchanged. They are dynamic systems influenced by the constant tug-of-war between pressure, temperature, and the movement of the ice above. These forces act together to create rivers that shift slowly over time, adjusting to new conditions as the ice evolves. The weight of the ice also creates friction against the bedrock. As the ice moves, the bottom layers rub against the rock surface. This friction may seem insignificant given how slowly the ice moves, but the sheer mass involved ensures that even this slow movement generates heat. This frictional heat adds to the geothermal warmth and pressure melting already occurring at the base. In certain regions, the friction becomes a primary contributor to the presence of liquid water. In others, it simply helps maintain the temperature balance. Either way, the friction produced by the ice movement under its own weight plays a role in sustaining the hidden rivers. In addition to generating heat, the movement of the ice sheet can affect the distribution of stress across the bed. When the ice flows around a ridge or over an uneven surface, the pressure changes. Water might accumulate on one side of the ridge, creating a small reservoir. If the pressure becomes high enough, the water may push through a weak point, carving a new pathway. This process can create sudden shifts in the hidden river network. Water can drain from a subglacial lake in a matter of days or weeks, releasing enough liquid to raise or lower the ice surface above. These changes can be detected by satellites, providing one of the few direct signs of activity in the hidden world beneath the ice. The immense weight also compresses the sediments beneath the bedrock. These sediments may have accumulated long before the ice sheet formed. As the ice presses down, it compacts the sediments, reducing the spaces between the particles. This compaction can influence how water moves through the sediments. In some cases, the water flows more easily through compacted layers. In others, the sediments become so dense that water cannot pass through them at all, causing it to divert into different routes. These variations create a complex system of permeability that determines where water collects, how it drains, and how it interacts with the bedrock. The pressure from above shapes not only the physical environment but also the chemical environment. When water flows under high pressure, it interacts with minerals in the bedrock differently than it would on the surface. It can dissolve certain minerals more easily due to the pressure and temperature conditions. These dissolved minerals may then precipitate out in other regions where the pressure changes, altering the composition of the sediments. This ongoing chemical activity provides additional clues about the history of the bedrock and the movement of the water. One of the most significant effects of the weight is how it influences the hydraulic potential beneath the ice sheet. This is a measure of how water flows based on pressure and elevation. Under the ice, pressure from the overlying mass contributes more to hydraulic potential than elevation alone. In many cases, water flows uphill relative to the bedrock simply because the pressure above that area is lower. This counterintuitive flow pattern is one of the defining features of subglacial hydrology. It means water can travel in directions that would be impossible on the surface. The hidden rivers navigate this potential landscape, seeking the paths where pressure and elevation combine to create the easiest flow. Because of this pressure-driven landscape, the hidden rivers do not always follow the simplest routes carved by bedrock. They follow the routes carved by pressure gradients. As the weight of the ice shifts, so does the pressure. Over long periods, these changes reshape the network. Water may abandon an old route and carve a new one. Small shifts in ice thickness, movement, or temperature can redirect flow in subtle but important ways. These changes happen slowly on the scale of human perception, but on geological timescales they play a significant role in shaping the subglacial environment. The pressure also affects how the ice transitions from solid to liquid and vice versa. In some regions, water may freeze onto the base of the ice sheet, adding new layers of ice from below. This process is called basal freeze-on. It creates patterns in the ice that can be detected through ice cores. These freeze-on layers hold clues about the conditions at the base. They show when water was present, when it froze, and how the system has changed over time. Understanding these patterns helps researchers reconstruct past climates and glacial movements. Despite the massive weight of the ice, the bedrock beneath it isn't always static. It shifts slowly over time in response to the pressure. This process is known as isostatic adjustment. When the ice grows thicker, the bedrock sinks. When the ice thins, the bedrock rebounds upward. These movements happen very slowly but have a significant effect on the hydrology beneath the ice. Changes in bedrock elevation alter the hydraulic potential, shifting the pathways of the hidden rivers over long time periods. The bedrock responds to changes in the ice, and the water responds to changes in both. Even though the weight of the ice creates a harsh environment, it also provides protection. The pressure prevents the bedrock from fracturing too easily. It prevents large voids from forming. It suppresses seismic activity in some regions by keeping rock layers tightly pressed together. This stability helps the hidden rivers maintain their pathways despite the forces acting on them. The water may move slowly or rapidly depending on the conditions, but the environment remains consistent enough to sustain these pathways for long periods. The ice sheet itself also responds to changes in the subglacial water system. If a hidden river expands, the lubrication beneath the ice increases. This can cause the ice above to move more quickly. In some cases, entire glaciers accelerate because of changes happening far below them. These shifts can influence the stability of the ice sheet as a whole, especially in regions where the ice meets the ocean. Understanding the weight and its effects helps researchers predict how the ice sheet will respond to future changes in climate and water flow. Despite all these interactions, the environment remains extremely difficult to study directly. The pressure is so great that any drilled hole risks closing before instruments can be lowered into it. The ice deforms continuously, making long-term installations challenging. Instruments must withstand extreme pressure, cold, and the possibility of being crushed if the ice shifts. Even if a sensor is successfully deployed, the pressure from the surrounding ice may alter its readings or damage its components. These challenges explain why our understanding of the hidden rivers remains incomplete, despite years of research. Still, the weight of the ice gives researchers clues they can measure. Satellite observations reveal subtle changes in surface elevation caused by shifts in water beneath the ice. Radar instruments can detect areas where the ice flows more quickly due to increased lubrication. Seismic tools can measure vibrations and determine whether the base is frozen or lubricated by water. These indirect measurements allow scientists to build models that approximate the conditions beneath the ice, even if they can't observe them directly. The weight pressing down also acts as the primary force that sets the stage for everything happening deeper below. It determines the melting point. It shapes the bedrock. It influences the flow. It controls the pressure gradients. It dictates where water can persist. It is one of the main reasons the hidden rivers exist at all. Without it, the environment beneath the ice would look entirely different. As we continue to move through this hidden landscape in our exploration, the next natural step involves understanding the subtle but steady warmth rising from beneath the Earth's surface, and how that warmth interacts with the immense pressure above to maintain the rivers flowing in the darkness. When you imagine a place buried beneath kilometres of ice, the assumption is that everything down there must be frozen in absolute stillness. The cold at the surface alone is enough to shut down almost anything mechanical, so it feels natural to think the deeper layers would be even colder. But the environment beneath the polar ice sheets isn't simply the result of what happens above. It also reflects what rises from below, from the slow, persistent heat that has been leaking out of the Earth's interior since the planet first formed. This hidden heat plays a quiet but essential role in allowing liquid water to survive where logic suggests it should freeze instantly. Unlike the warmth created by sunlight or weather patterns, geothermal heat doesn't fluctuate with the seasons. It doesn't care if the sky above is clear or stormy, or whether the winds are calm or violent. It rises at a steady pace from the Earth's mantle, moves through the crust, and enters the base of the ice sheet with a patience that matches the timescale of geology. This warmth is not intense. It won't melt the ice rapidly or create gushing streams on its own. Instead, it provides a subtle but persistent foundation of heat that prevents the deepest layers of the ice from reaching the same extreme cold as the surface. The surface of Antarctica can fall to temperatures far lower than anything found in the Arctic. In some regions, the winter cold can drop so far below freezing that it pushes the limits of what scientific instruments can measure without failing. Yet a few kilometres below, right where the ice meets rock, the temperature rises significantly. It doesn't rise to anything comfortable or warm in the human sense, but it reaches a level where the combination of heat and pressure becomes enough to maintain liquid water. This warmth doesn't create a tropical environment or anything remotely close. It simply nudges the temperature at the base to the edge of melting, where ice transitions into water and tiny channels begin to form. The amount of geothermal heat varies across the polar regions. It depends on the thickness of the crust, the composition of the rock, and deeper geological structures such as rift zones or volcanic features. Some areas beneath the ice sheet receive more heat than others, simply because the crust is thinner there, allowing warmth from the mantle to rise more efficiently. In regions where the crust is thicker, the geothermal heat comes through more slowly. But even in the coldest zones, this upward flow of heat still contributes to maintaining the delicate balance at the base of the ice sheet. In Antarctica, certain regions have surprisingly high geothermal heat flow. For example, the West Antarctic Rift System is known for its thinner crust and increased geothermal activity. This rift zone is not an active volcanic region in the dramatic sense, but the geology is lively enough that the crust carries more warmth upward. This heat influences how the ice above behaves, making it more likely for water to accumulate at the base and for large subglacial lakes to form. Some of the most well-studied subglacial lakes owe their existence not just to pressure melting, but also to the quiet presence of geothermal heat rising from below. The presence of geothermal warmth doesn't always mean the same thing across the ice sheet. In some areas, the heat rises in small, concentrated patches. These hotspots might create localized melting that forms isolated ponds or channels of liquid water. In other areas, the heat is more evenly distributed, contributing to broader regions of basal melting. The hidden rivers that form in these environments follow the patterns set by both bedrock topography and geothermal input. They may begin as small trickles fed by a localized hotspot, or as widespread melt that collects gradually and moves along a gentle slope. One of the reasons geothermal heat matters so much is that the ice sheet acts as a near-perfect insulator. Although the ice above is cold, the sheer thickness of it prevents heat from escaping quickly. The ice traps the warmth below, creating an environment where even small amounts of geothermal energy can accumulate. If the ice were thinner, the heat would dissipate toward the surface more easily. But with kilometers of frozen mass sitting on top, the heat has nowhere to go except into the bottom layers of the ice sheet. This insulation effect makes the basal temperature surprisingly stable. While the surface of the ice sheet might shift wildly between seasons, the base remains relatively steady. The variations in geothermal heat flow are more significant than any seasonal temperature changes from the surface. This means that the environment supporting the hidden rivers is shaped far more by the Earth's interior than by the atmosphere above. The heat rising from below affects the structure of the ice in several ways. First, it determines how close the ice base is to the melting point. In regions where geothermal heat is stronger, the basal ice may be at or near melting throughout the year. In places with lower heat flow, the ice might remain frozen to the bedrock. Even small differences in heat can shift a region from frozen to melting, altering how water moves and where rivers can form. Second, the geothermal heat influences the strength and character of the bedrock. Rock that receives consistent heat from below may undergo slight temperature-driven changes that affect how easily it erodes. Softer or fractured rocks interact differently with the flowing water. They may contribute more sediments to the water, shaping the riverbed and influencing where the water can carve deeper channels. The heat itself is not evenly distributed across the continent. Measurements taken from boreholes drilled through the ice show a range of geothermal values. Some areas might have as much as several hundred milliwatts per square metre of heat flow, while others have far less. These differences create a mosaic of thermal conditions beneath the ice sheet. Each region develops its own pattern of water flow, depending on how much geothermal warmth it receives. In locations where the geothermal heat is relatively high, the result can be persistent melting and stable channels of flowing water. These regions can host large subglacial lakes that remain liquid year-round. The water in these lakes may circulate slowly, fed by meltwater from the surrounding ice, and drained by the hidden rivers leading out of them. In regions with lower heat flow, the water may freeze more easily, creating frozen patches where the drainage system becomes intermittent or fragmented. Despite these variations, geothermal heat alone rarely melts the ice rapidly. It works gradually, balancing against the cold from above and the pressure from the ice. This balance creates a narrow temperature window where liquid water can survive. If the geothermal heat were significantly higher in certain regions, it could lead to more dramatic melting, but the insulating effect of the ice moderates the temperature. The ice sheet absorbs any excess heat, distributing it across the lower layers and preventing sudden changes. One of the most interesting aspects of geothermal heat beneath the ice is how it interacts with pressure. The pressure from the ice sheet lowers the melting point, allowing water to form even when the temperature remains below 0 degrees Celsius. Geothermal heat pushes the temperature upward. Together, these forces create an environment where water can exist at temperatures well below what most people would consider normal for liquid water. This combination explains how hidden rivers can flow under the ice without freezing solid. The geological context of Antarctica contributes heavily to this situation. The continent sits atop a complex mosaic of ancient cratons, mountain ranges buried under ice, rift zones, and regions of thinner crust. Each of these features influences how heat moves upward. Some of the most well-known subglacial lakes, such as Lake Vostok, may owe their stability in part to elevated geothermal heat in the surrounding crust. Even slight increases in heat flow can keep a massive lake liquid, allowing it to remain a unique and isolated environment for millions of years. There are regions where geothermal heat flow is so low that the base remains frozen to the bedrock. But even in those places, small pockets of meltwater may form at times due to pressure or friction from ice movement. These pockets may move slowly and form part of a broader drainage network. They connect with other regions where geothermal heat is stronger, allowing water to travel across long distances beneath the ice sheet. Water that forms in warmer zones may move into colder areas, carrying heat with it. This heat transport can prevent the surrounding ice from freezing as quickly as it otherwise might. The flowing water distributes the geothermal energy across the basin, helping maintain liquid conditions even in regions where the heat flow alone would be insufficient. The transport of heat by water flow is another important factor in supporting the hidden rivers. The influence of geothermal heat also plays a role in shaping the chemical composition of the water. As the water moves through sediments and rock heated from below, it dissolves minerals more easily. These minerals change the water's properties. They may lower the freezing point slightly, They may affect how the water interacts with the bedrock. They may serve as potential energy sources for microbial life if such organisms exist in these environments. The chemical composition of the water becomes distinct from anything on the surface, shaped by the unique interaction of pressure, heat, and geology. Although geothermal heat is steady and predictable in many ways, it can also create unexpected variations. In some regions, the geological structures beneath the ice are poorly understood. There could be zones of higher heat flow that create localized melting far larger than expected. These areas may carve larger channels or create lakes that remain hidden until satellites detect slight changes in ice elevation. In other areas, the heat flow may be lower than predicted, leaving regions colder and less active in terms of hydrology. The variability of geothermal heat means that the hidden rivers beneath the ice are far from uniform. Researchers have used a variety of methods to study geothermal heat beneath the ice sheet. Boreholes provide direct measurements in specific locations, but drilling to the base of the ice is difficult and rare. Radar surveys help reveal variations in ice thickness and bedrock structure that can suggest higher or lower heat flow. Seismic data offers clues about the temperature of the crust and the presence of geothermal anomalies. Together, these tools provide a patchwork of information that scientists use to construct models of heat distribution beneath the ice. Despite these advances, large sections of the bedrock remain poorly mapped in terms of geothermal activity. The heat flow may vary in unexpected ways across the continent, influencing water flow patterns in ways researchers have yet to discover. As new technology becomes available, scientists hope to gain a clearer picture of the geothermal landscape and its role in supporting the hidden rivers. The consistent upward flow of heat ensures that the environment at the base of the ice remains active long after the surface has settled into stillness. It provides the energy needed to maintain the hidden rivers, support subglacial lakes, and shape the hydrological network. Without this heat, the pressure from above might not be enough on its own to sustain liquid water over long periods. The geothermal warmth stabilizes the system, giving the water the temperature support it needs to remain liquid. As we continue following the forces shaping this hidden world, the next step leads naturally into understanding why our tools struggle to reach these rivers, even with all the knowledge gained about pressure, geothermal heat, and ice movement. The difficulties of accessing this environment involve more than distance. They involve physics, engineering limits, and the risks of disturbing a delicate balance that has existed for ages. Reaching the hidden rivers beneath the polar ice sheets is one of those challenges that sounds straightforward from a distance. Drill down, send instruments, take measurements, bring back data. It feels like something humanity should be able to do with enough determination and a good collection of machines. After all, we've built telescopes that can detect galaxies so far away, they exist mostly as faint whispers of light. We've explored the deepest parts of the ocean using pressure-resistant vessels. We've sent spacecraft beyond the edges of the solar system. Compared to those achievements, drilling through ice might seem like a manageable task. But the reality beneath the polar ice sheets is nothing like what happens on a frozen lake or a glacier near a mountain range. The deeper you go, the more the rules change, and the more obvious it becomes why our tools still can't quite touch the world hidden below. One of the first challenges involves simply reaching the drilling site. The regions where scientists want to drill are often some of the most remote places on Earth. Reaching them requires traversing long stretches of snow and ice, sometimes using specialized vehicles capable of handling deep fractures and unstable terrain. These journeys can take days or weeks, depending on weather, distance, and the condition of the snow surface. Every piece of equipment must be transported carefully, often by aircraft or over-ice convoys. Fuel, food, tools, clothing, housing, scientific instruments, everything must be brought in because nothing exists there except wind and ice. Once the equipment arrives, the next difficulty begins. The ice sheet is not a stable platform. It is always shifting under its own weight, always responding to temperature changes and stress variations. Building a camp on top of it means accepting that the ground beneath you is not solid in the traditional sense. Drill towers must be anchored securely. Shelters must withstand winds that can pick up enough snow to bury equipment in a single storm. Power systems must remain functional in temperatures that can disable batteries and crack cables. Simply keeping the equipment operational can be a full-time task. Then comes the drilling itself. Traditional drills that work on rock, soil, or permafrost cannot simply be repurposed for 3 kilometers of polar ice. Ice behaves very differently from typical geological materials. It melts, refreezes, fractures, and flows. Drilling into it requires specialized techniques, and each technique carries its own set of challenges. One of the most widely used approaches is hot water drilling. In this method, water is heated to high temperatures and pumped through a nozzle that melts a hole straight downward. This method can create a relatively rapid descent through the ice, and it avoids the problem of generating ice shavings that need to be removed. But hot water drilling demands vast amounts of fuel. The water must stay hot the entire time, and the circulation system must remain functional for long periods in extreme cold. If the system stops even briefly, the hole begins to refreeze almost immediately. This means the entire operation must run continuously until the drilling is complete. Another approach involves mechanical drilling using large rotating bits. But mechanical drills face an entirely different set of issues. The bits can freeze to the surrounding ice. The borehole walls can deform or collapse. The drill can get stuck if the ice refreezes around it. Mechanical systems also require lubrication, which introduces the risk of contamination. Any oil or lubricant entering the water beneath the ice would alter the pristine environment scientists are trying to study. Sterility is another reason our tools can't simply be lowered into the hidden rivers. The water beneath the ice has been isolated from the surface for thousands, possibly millions of years. It contains chemical signatures and possibly biological ecosystems that are unique to that environment. Introducing modern microbes, even in small numbers, could contaminate the system permanently. Once contaminated, the site would no longer provide accurate scientific data. For this reason, drilling systems must be cleaned, sterilized, and designed to avoid introducing any foreign materials into the subglacial water. Hot water drilling is considered relatively clean, but even it must go through extensive treatment. The water used in the drill must be filtered, heated, pressurized, and sterilized with ultraviolet light. All hoses and equipment must be disinfected. The entire system becomes a mobile sterilization facility. Maintaining this level of cleanliness in the harshest climate on Earth is an immense challenge. Even with these precautions, the risk of contamination remains a concern. Pressure adds yet another complication. At the base of the ice sheet, the pressure from the overlying layers is extreme. This pressure lowers the melting point of ice and affects how water behaves. When a borehole reaches this zone, the pressure difference between the water in the river and the water in the drill system can create instability. If the borehole penetrates into a pressurized pocket of water, it could cause water to rise rapidly through the hole, threatening the stability of the equipment. In extreme cases, it could flood the drill site, damage instruments, or freeze rapidly if the water encounters colder layers of the borehole. Communication systems also struggle at these depths. Signals sent through kilometers of ice can weaken or distort. Instruments lowered into the borehole need reliable communication lines to transmit data and receive commands. These lines must be strong enough to survive extreme cold, pressure changes, and potential bending from ice movement. Fiber optic cables and insulated wires must be specially designed and tested. Even then, failures can occur with little warning. A single damaged cable could render a mission's data collection impossible. Another limitation comes from the fact that ice deforms continuously. A borehole that is circular and smooth at the moment of drilling may become distorted as the ice flows around it. Within hours or days, the hole can narrow enough to trap instruments. In some cases, previously drilled boreholes have been lost entirely as the ice closed around them. This phenomenon makes long-term installations challenging. Instruments that might collect data for months or years in other environments must be designed to survive being slowly squeezed by the surrounding ice. The deeper the drill goes, the more difficult it becomes to maintain alignment. Ice sheets are not perfectly vertical, and bedrock topography can cause the entire mass to shift in subtle ways. Drilling straight down into a precise location becomes a complex engineering problem. A small deviation near the surface can result in a large deviation near the bottom. Reaching a target, such as a subglacial river only a few meters wide, requires careful navigation through layers that are constantly moving. Even when a borehole successfully reaches the bottom, the challenges continue. Instruments lowered into subglacial water must withstand pressure that would crush ordinary devices. They must operate at temperatures near freezing without failing. They must avoid being clogged by sediments or becoming lodged in narrow channels. They must collect data effectively and send it back through kilometers of ice without losing signal strength. Designing such instruments demands engineering solutions that stretch current capabilities. Another major obstacle is time. Drilling can take days, weeks, or even months depending on the method used and the depth of the ice. The longer the operation continues, the greater the risk of equipment failure, weather disruptions, or logistical complications. Storms can delay progress. Fuel supplies can run low. Crevasses can shift. Teams must work in extreme cold for long periods, often in isolated conditions. Human endurance becomes a factor as well, because scientists and engineers must remain alert, focused, and healthy in a place where the environment offers no comfort or margin for error. Funding and resource limitations also play a role in hindering direct exploration. The cost of mounting a drilling mission to the bottom of a major ice sheet is immense. It involves specialized equipment, transportation, personnel, and support systems. These missions require years of planning, design, and testing before they even reach the field. Only a handful of such missions have been attempted, and even fewer have succeeded in reaching subglacial lakes or rivers without contamination. Because drilling remains so difficult, researchers rely heavily on remote sensing techniques. Radar systems mounted on aircraft can penetrate the ice and detect reflections from the bedrock or liquid water beneath it. These reflections reveal the shape of the bed, the presence of lakes, and the potential pathways of hidden rivers. However, radar cannot measure everything. It cannot detect fine-scale details. It cannot sample the water directly. It cannot capture the chemistry, biology, or precise temperature of the environment. Radar offers a map, not a direct understanding. Satellites provide another key tool. By measuring tiny variations in the elevation of the ice sheet's surface, satellites can detect when subglacial lakes fill or drain. When a lake fills, the ice above may rise slightly, like a mattress supported by extra pressure. When it drains, the ice may sink. These subtle movements, measured from space, reveal the activity of the water system beneath. But satellites cannot see inside the lakes or rivers. They cannot measure flow rates directly. They cannot sample water or sediments. Seismic techniques help as well. By sending vibrations through the ice and analysing how they travel, researchers can infer where the ice is frozen to the bedrock and where water might be acting as a lubricant. These signals help identify potential river pathways, but the resolution is limited. The results often require interpretation and modelling, and there is no guarantee they capture the full complexity of the subglacial environment. Computer models pull together all available data to simulate how water flows under the ice. They incorporate ice thickness, bedrock elevation, pressure gradients, geothermal heat, and other variables. These models generate predictions about where rivers might be, how they behave over time, and how they respond to changes in climate or ice movement. But models depend on assumptions and approximations. They provide guidance rather than certainty. Even with all these tools, radar, satellites, seismic measurements, models, the simple fact remains: we have never sent an instrument into most of the hidden rivers beneath the ice. We have touched only a handful of subglacial lakes, and even those were reached under extraordinary circumstances. The majority of the drainage system remains untouched, unseen, and unexplored in any direct sense. Engineering solutions continue to advance, but each new idea faces the same set of obstacles. Autonomous probes capable of melting their way downward have been proposed. These probes would carry their own heat sources, sensors, and communication systems. They would avoid drilling limitations by melting through the ice gradually. But the challenges of maintaining sterilization, surviving pressure, and transmitting data upward remain. Some concepts involve using lasers or microwave energy to melt the ice. Others suggest using robotics inspired by deep-sea exploration. Yet for now, each concept faces barriers that must be solved one at a time. Despite these delays, the motivation to reach the hidden rivers remains strong. Scientists want to study the chemistry of the water, the sediments, the temperature gradients, and the flow patterns. They want to determine whether life exists in these isolated environments. They want to understand how the hidden rivers influence the stability of the ice sheet and the long-term patterns of sea level rise. But for now, our tools are not quite capable of touching these rivers safely and reliably. The limitations are not permanent. They reflect the complexity of the environment, the slow pace of technological advancement in extreme settings, and the need for careful thinking when exploring places that have remained undisturbed for ages. The next steps in this exploration involve designing systems that can withstand pressure, avoid contamination, navigate narrow channels, and return data across vast distances of ice. These breakthroughs will come, but they require patience. As we move into the next part of this journey, it becomes clear that reaching the rivers is only part of the challenge. Even when we do manage to touch them, the environment around them can freeze equipment before it has a chance to function. The next step in understanding this hidden world involves examining why machines struggle so much in these cold, pressurized, and unpredictable conditions, and why so many designs fail before they even begin. Working with machinery in environments that stay below freezing is already a major engineering challenge. Cars struggle in mild winter conditions, batteries weaken, metal contracts, lubricants thicken, electronics respond slowly or unpredictably. Those are the issues people deal with in places where the cold is still within reach of ordinary experience. But the temperatures on the surface of Antarctica drop far lower than anything most machines are built to tolerate. Instruments that work reliably in cold mountain climates or Arctic research stations become unpredictable once exposed to polar plateau conditions. And if these machines struggle above the ice, it becomes clear why they face even more severe problems when tasked with reaching the hidden rivers buried far below. The first major issue machines face is loss of power. Batteries drain rapidly in extreme cold. The chemical reactions that generate electricity slow down because the molecules inside the battery move less efficiently. This problem is manageable when the temperature is a few degrees below freezing, but at polar temperatures the effect becomes extreme. A battery that might last hours at room temperature can fail in minutes in the coldest regions of Antarctica. Even insulated battery packs struggle unless they generate their own heat or remain constantly warmed by external systems. Heating these systems requires additional power, which increases the energy load on the mission as a whole. Extra fuel must be transported, which adds weight and complexity. Every solution to one problem introduces new challenges that must be managed carefully. If the heating system malfunctions, the internal electronics cool quickly and shut down. If the insulation fails, condensation may form and freeze inside the housing, damaging sensitive circuits. Cold affects every part of the power system, from the main battery to the smallest wires. Mechanical components respond even more dramatically. Metal contracts in the cold. Small tolerances that function well at room temperature become too tight when everything shrinks slightly. Moving parts seize or grind. Bearings stiffen. Lubricants designed for cold regions may solidify. Even materials chosen specifically for low-temperature conditions can still react unpredictably when faced with the extreme cold found on the polar plateau. Machinery becomes brittle, and slight impacts that would be harmless elsewhere can cause fractures. The deeper challenge comes from the way cold interacts with moisture. Any liquid, Even a trace amount can freeze rapidly in these conditions. If a machine includes hydraulics, pumps, or any mechanism that uses fluids, those fluids become a liability. They can freeze inside tubes or form ice crystals that damage valves. Engineers use specialized hydraulic fluids for cold environments, but there is a limit to how cold these fluids can go before they lose their usefulness. The polar environment tests those limits constantly. Electronics also face difficulties. Cold temperatures affect conductivity, resistance changes, timing circuits drift, displays become sluggish or unresponsive. Sensors that depend on precise electrical behavior may produce inaccurate readings. Connections between components contract, loosening or cracking solder joints. Even if the electronics themselves are built to operate in the cold, the cables that connect them may become stiff or brittle, causing internal damage when bent or flexed. Moving from the surface into the drilling process adds another layer of complications. Hot water drilling systems rely on pumps, hoses, and heating units. All of these components must operate continuously to prevent the water from cooling. If the water cools, ice begins to form inside the system. Once ice forms inside a hose or pump, it can block the flow, cause pressure buildup, or damage the machinery. Keeping the water hot enough to stay liquid requires significant power, careful monitoring, and precise coordination between technicians. Every moment of downtime increases the risk of the system freezing. The hoses themselves are vulnerable. They must withstand high pressures while remaining flexible at extremely low temperatures. Materials that are flexible in moderate cold often become rigid at polar temperatures. If a hose becomes too stiff, it can crack when moved or kink during deployment. A single crack in a hose carrying pressurized heated water can shut down the entire operation. Because drilling teams must operate continuously, day and night, any hose failure becomes a major setback. Mechanical drills face their own challenges. Drill bits can freeze to the surrounding ice. Drilling fluid may freeze into place before it reaches the cutting head. The cable supporting the drill can become brittle, and the winches that raise and lower the equipment can jam. Drills generate heat through friction as they cut, but that heat dissipates quickly into the surrounding ice. If the balance is not maintained, the drill can become encased in ice before it's retrieved. Thermal drills that melt their way downward risk refreezing behind themselves. If the drill's heat output is not sufficient to keep the entire borehole open, ice begins to close in around the drill. These systems must maintain a precise thermal gradient to avoid becoming trapped. If the hole narrows too quickly behind them, the cable delivering power and communication may become stuck, ending the mission prematurely. Another major challenge comes from the fact that the deeper the machinery goes, the colder the surrounding ice tends to be until it reaches the very bottom. Machines travelling through the ice face increasingly harsh conditions until they approach the zone where pressure and geothermal heat provide some relief. But equipment never reaches that zone without passing through the coldest layers first. These layers can cause machinery to freeze solid before it reaches its destination. Pressure plays a role as well. As machinery descends deeper, the pressure from the surrounding ice increases. This pressure can compress housings, deform components, and squeeze any trapped air inside devices. If a housing collapses even slightly, it can compromise seals, allowing moisture to enter. If moisture freezes inside the electronics or mechanical parts, the device may stop working. Designing housings that can withstand this pressure without becoming too heavy is a constant engineering trade-off. Communication cables running through the drill hole face similar pressures. The cable must remain flexible enough to be deployed but strong enough to resist being crushed. It must transmit data reliably across long distances while enduring temperature shifts and bending forces. If ice forms around the cable, the surrounding pressure can pinch it slowly until internal fibers break. Even small imperfections in the insulation can become failure points when the ice applies pressure continuously. The risk of refreezing affects not only the machinery but also the drill hole itself. Once the hole is created, it begins to cool immediately. The surrounding ice absorbs heat quickly. If the hole is narrow, the heat dissipates even more rapidly. Teams must either keep the hole open with constant circulation of hot water or deploy instruments before the hole narrows too much. This creates a narrow time window during which all operations must be completed. If the hole refreezes faster than expected, instruments may become trapped and the mission may need to be abandoned. Deploying instruments involves its own risks. Sensors lowered into the borehole must endure not only the cold, but also the possibility of encountering soft sediments, pressurized water, or unexpected obstacles. If the sensor reaches a water-filled cavity, the sudden change in environment can cause thermal shock, rapid temperature shift that stresses electronic components. Condensation may form inside housings and freeze instantly, damaging delicate circuits. Instrumentation sent into subglacial water must also avoid being coated with ice. When the device enters the water, it may carry a thin layer of cold air around it. As the device warms up slightly from contact with water, that air can cause condensation. The condensation can freeze to the housing. If the instrument is removed too quickly, the sudden exposure to colder ice layers may cause the ice to expand or crack the outer shell. Engineers must design instruments that eliminate these risks as much as possible, though eliminating them entirely remains extremely challenging. The cold also affects the human operators. Technicians must work in an environment where exposed skin can freeze rapidly. They must handle metal components that can cause frostbite on contact. Tools become stiff or brittle. Gloves make fine motor tasks difficult. The cold reduces dexterity and increases fatigue. Workers must take frequent breaks to warm up, slowing down the operation. They must monitor equipment continuously, adjusting for temperature fluctuations and addressing issues before they become critical. Even vehicles used for transport face difficulties. Engines may not start without preheating. Fuel can gel. Tyres can lose pressure. Tracks may freeze. Lubricants may thicken. The equipment needed to support drilling missions requires constant maintenance and supervision. Something as simple as a frozen fuel line can delay operations for hours. When machinery does reach the bottom of the borehole, the challenges change but do not disappear. The instruments must navigate a water system that may be only a few centimetres thick or could open into a large lake. They must avoid stirring sediments that could cloud sensors or clog filters. They must operate autonomously if the connection cable becomes unreliable. They must record data and return it before the environment damages the equipment. Efforts to create autonomous melting probes, sometimes called cryobots or ice-penetrating robots, face additional complications. A cryobot must carry its own heat source, either electrical or nuclear, and melt its way downward gradually. It must maintain a smooth borehole to prevent being trapped. It must communicate through the ice, which absorbs signals and restricts the possible frequencies that can be used. The cryobot must also avoid contaminating the environment with any residue from its internal heat source. Sterilization becomes even more complicated because the probe's heat can cause chemical reactions that release trace contaminants. Even if all those technical challenges are addressed, the cryobot must be able to stop, collect data, and return information without becoming lodged in sediments or trapped in narrow channels. A probe that melts downward may slide into soft mud or silt at the base, making movement difficult. If the probe sinks too deeply into sediment, it may not be able to move at all. Retrieving a stuck probe would be nearly impossible. Engineers must therefore design these machines with careful consideration of buoyancy, mobility, and safety. The complexity of this requirement is one of the reasons these missions remain largely experimental. Another difficulty comes from the unpredictability of the subglacial rivers themselves. Unlike surface rivers, they do not carve wide channels filled with flowing water. Some may be thin films of water only millimeters thick. Others may be larger channels filled with sediments, silt, or debris. The water may be under pressure, ready to surge if disturbed. A probe entering such a region could be pushed unexpectedly or damaged by turbulent flow. Sediment-laden water can abrade surfaces, reducing the lifespan of sensors. Chemical conditions may be corrosive. The environment may contain minerals that interact with metal surfaces in unexpected ways. When machinery is designed for extreme environments, engineers often draw lessons from deep-sea exploration. But the environment beneath the ice shares characteristics with deep-sea conditions while adding its own unique challenges. Deep-sea vessels experience high pressure but operate in liquid water rather than solid ice that can squeeze gradually over time. They do not need to worry about refreezing or drilling. They do not need to worry about borehole collapse. They are not forced into narrow pathways or sediment-filled channels. The under-ice environment is more constricted, colder, and more variable. One of the reasons these challenges persist is that testing options are limited. Engineers cannot easily simulate the exact conditions found beneath the ice sheet. Laboratory setups can replicate cold temperatures, pressure, or ice movement individually, but they cannot recreate the combination of all these factors working together. As a result, the first real test of a system often happens in the field, where malfunctioning components may be difficult or impossible to repair. A single oversight in design or testing can jeopardize years of preparation. Despite these obstacles, each failed or stalled mission contributes valuable knowledge. Engineers learn which materials withstand the cold best, which designs hold up under pressure, and which systems fail most often. They refine insulation, develop new lubricants, strengthen housings, improve communication systems, and modify drill techniques. Progress happens gradually as each attempt adds another layer of understanding. But even with all this progress, the fact remains that many machines freeze before they begin. They fail not because of incompetence or oversight, but because the environment is exceptionally unforgiving. The cold reaches into every system, every material, every design choice. The pressure shapes every decision about structure and housing. The ice itself works against every effort to penetrate it. And the hidden rivers remain beyond the reach of most machines built so far. As this exploration continues, the next step naturally leads into understanding the risks associated with disturbing these waters in the first place. Even if we solved every technical challenge, reaching these rivers raises questions about what might happen if their isolation is disrupted. The environment has remained sealed beneath the ice for ages, and any intrusion carries consequences that reach beyond engineering and into ecological and geological considerations. When researchers talk about accessing the hidden rivers beneath the polar ice, the conversation usually centers on the engineering challenges: the cold, the pressure, the distance, the ice that shifts and closes around boreholes, the machines that freeze or malfunction. These difficulties are enormous, but they are not the only reasons we hesitate to touch the waters concealed under all that ice. Another reason, one that scientists discuss carefully and often with a kind of quiet seriousness, involves the risks that come with disturbing an environment that has been sealed off for ages. The water beneath the ice has been isolated for so long, living under conditions so different from anything at the surface, that even a small intrusion could create consequences we do not fully understand. The concept of ancient waters might sound dramatic, but in this case, it is accurate. The water at the base of the ice sheets may have been trapped for tens of thousands of years, possibly longer in some regions. It has not mixed with surface water. It has not been exposed to sunlight, oxygen, or anything carried by the wind. It exists in a state of near-complete isolation. This isolation shapes its chemistry, its temperature, its structure, and any biological community that might exist within it. Disturbing that environment is not simply a matter of drilling through ice and collecting a sample. It is a step into a world that has remained untouched since long before humans built cities or civilizations. One of the primary concerns involves contamination. Even the cleanest drilling system carries the risk of introducing foreign organisms or chemicals into the subglacial water. These contaminants may come from the drill apparatus, the water used for drilling, or the air inside the borehole. Microbes that live comfortably on the surface could survive the journey downward, carried by tiny pockets of warm water within the drill system, insulated by the very moisture that allows them to cling to surfaces. If these organisms reach the isolated water system below, they could disrupt any native ecosystem that exists there. They could multiply rapidly if the environment provides even a small amount of suitable conditions. This issue is not hypothetical. In other extreme environments on Earth, contamination has occurred before researchers fully understood how easily surface microbes can thrive in unexpected places. Experiments in deep mines, hydrothermal vents, and subglacial lakes have all revealed that microbes from the surface can survive in environments once believed hostile to anything except specialized native species. Because of these past experiences, scientists are extremely cautious. They understand that contamination is not simply a risk to scientific accuracy, it is a risk to the environment itself. Another concern involves the pressure difference between the hidden rivers and the boreholes used to reach them. When a borehole breaks into a pressurized pocket of water, the sudden release can change the balance of the system. The water might rush upward, bringing sediments and ancient materials with it. This upward movement could disrupt the drainage network beneath the ice. It could cause a subglacial lake to drain more rapidly than usual, affecting the movement of the ice sheet above. In extreme cases, it might alter the distribution of water across wider regions of the basal layer, influencing where ice slides more easily and where it remains frozen to the bedrock. Such a disturbance could have cascading effects. A sudden shift in water flow could accelerate the movement of nearby glaciers. It could create new channels or close existing ones. The drainage system beneath the ice, though hidden, is interconnected. A disruption in one location could have consequences far away, even if no one sees the change directly. Researchers must consider these risks carefully when planning any mission that might tap into the hidden rivers. Chemical disruption poses another set of risks. The water beneath the ice may contain chemical compounds that have remained stable for long periods. It may hold minerals dissolved from the bedrock, gases trapped under pressure, or organic material preserved by cold temperatures. Introducing surface water or drilling fluid could alter these chemical balances. Even small changes might cause reactions that disrupt sediments or shift the composition of the water. If the water contains delicate biological systems adapted to stable conditions, even a slight chemical disturbance could have significant consequences. If microbial life exists in these waters, the risks grow more complex. The organisms living there would have evolved without exposure to the surface world. They might rely on specific minerals, chemical gradients, or energy sources that are disrupted by the introduction of foreign matter. They might be vulnerable to even trace amounts of oxygen. They could be outcompeted by surface microbes introduced accidentally through the drilling system. These possibilities make researchers cautious not just from a scientific standpoint, but from a responsibility standpoint. They want to learn about these environments, not damage them. Beyond biological risks, there are geological considerations. The hidden rivers occupy channels carved by pressure, temperature gradients, and the shape of the bedrock. If a borehole introduces heat into the system, the increased temperature could weaken ice in the surrounding area. This may change how water flows or how ice sits on the bedrock. If a drilling operation melts a larger cavity than expected, that cavity might collapse or create a small void that alters pressure gradients. Even a small void might be enough to redirect water over long periods. These changes could influence the stability of the ice sheet. If the water begins to flow more quickly in certain areas, it could lubricate the base of the ice and increase glacier speed. If the water route shifts to a new region, it could weaken ice that has been stable for long periods. While these effects might be small at first, they could accumulate over time. Researchers cannot assume that once the drill leaves, the system will simply return to normal. The environment beneath the ice responds slowly but persistently to changes. One of the most serious risks involves the release of ancient gases trapped in the water or the sediments. Some regions beneath the ice may hold methane, carbon dioxide, or other gases produced by geological or biological processes. These gases remain stable under pressure and cold temperatures. But if drilling disturbs the sediments or alters the pressure balance, these gases could escape into the borehole. Depending on the concentration, they could pose hazards for equipment or researchers. Additionally, releasing these gases into the atmosphere could contribute to greenhouse effects, although the scale of such a release remains uncertain. There is also the risk of inadvertently triggering drainage events. Some subglacial lakes fill and drain periodically, altering the height of the ice surface above. These drainage events occur naturally, but drilling into a lake or river at the wrong moment might accelerate or delay such an event. The consequences of such a change could ripple across the local hydrological network. Researchers must plan operations carefully to avoid influencing the natural cycles of the hidden water systems. Another concern involves sediment disturbance. Sediments at the base of the ice sheet can be thick, soft, and easily displaced. They may settle into delicate layers reflecting thousands of years of environmental history. If drilling equipment disturbs these sediments, it can destroy valuable geological information. The layers might mix or collapse. Fine particles may cloud the water, making it difficult to analyze samples accurately. Sediment movement could also clog sensors or interfere with data collection. Even if the technological challenges were all solved, and even if contamination risks were minimized through rigorous sterilization, the deeper philosophical and scientific questions remain. Should we disturb these environments at all? The hidden rivers have existed without interruption for ages. They form part of a natural system that predates human activity by vast amounts of time. Some argue that disturbing these waters, even in the name of science, carries ethical implications. They point out that once the environment is touched, even if touched carefully, it can never return to a state of complete isolation. Others argue that learning about these environments is essential. The hidden rivers influence glacier movement, sea level rise, and long-term climate patterns. Understanding them could help scientists predict future changes in the ice sheets and their impacts on global coastlines. The water may hold microbial life that offers clues about how life can persist in extreme environments, potentially informing the search for life on other icy worlds. But even these researchers acknowledge the risks involved and approach their work with caution. The danger of stirring ancient waters is not just about contamination or mechanical disruption. It is about altering the balance of a world that has remained undisturbed for longer than human memory. It's about stepping into a system shaped by forces that operate on timescales humans rarely consider. It is about acknowledging that our presence can reshape environments, even without intending to. This sense of responsibility is why scientists take such care when planning every detail of a potential mission. They consider not just how to reach the water, but how to leave the smallest possible impact. They design equipment to minimize disturbance. They test sterilization methods repeatedly. They model pressure changes and water flow patterns. Every choice reflects a balance between discovery and preservation. As the exploration continues in this narrative, the next step naturally leads into understanding what might exist in these waters, and why disturbing them could reveal secrets not only about Earth's past, but also about what kind of life might endure in environments far different from the surface world. Life tends to find a way into places where it shouldn't logically exist. On the surface of the planet, there are creatures living in deserts with almost no water, organisms living inside volcanic vents where temperatures climb higher than the boiling point of water, and microbes that survive inside rocks deep underground with no sunlight at all. With that in mind, it becomes natural to wonder what might be living within the hidden rivers that sit trapped beneath kilometers of polar ice. The idea isn't just imaginative speculation. There are reasons grounded in evidence, chemistry, and biology to think that these dark waters may hold life, even if it's nothing like the life found on the surface. The first thing to consider is the age of the environment. The water deep beneath the ice has remained isolated for thousands or perhaps millions of years. If any organisms were sealed inside during that time, they would have evolved under extremely stable conditions. Their world doesn't experience day or night, summer or winter, wet seasons or dry seasons. It doesn't experience storms, floods, or droughts. Instead, the environment stays mostly consistent. shaped by steady cold temperatures, constant pressure, and slow-moving water that carries minerals from the bedrock. Organisms that adapt to such conditions could persist independently of the surface world, as long as their energy needs are met. On Earth, most life ultimately depends on sunlight. Plants capture sunlight and convert it into energy, forming the foundation of food chains. But in environments where sunlight never enters, deep oceans, underground caves, and certain regions of the polar ice, life has found alternative energy sources. Microbial communities in these places rely on chemical energy rather than light. This process, known as chemosynthesis, allows organisms to extract energy from chemicals such as sulfur, iron, hydrogen, or methane. Chemosynthesis has been observed in deep-sea vents, cold seeps, caves, and underground aquifers. If similar chemical sources exist beneath the ice sheets, microbial life could use them in the same way. The bedrock beneath the ice contains minerals that interact with water under pressure. As the water flows across these minerals, it dissolves tiny amounts of them. These dissolved compounds may include reduced iron, sulfur-bearing minerals, or organic matter trapped in sediments. Microbes adapted to use these materials could survive without sunlight. Some could consume iron. Others could feed on hydrogen released from the breakdown of certain minerals. Others might take advantage of organic molecules carried by water that has slowly melted from ice containing ancient dust, spores, or remnants of past ecosystems. Evidence supporting this possibility comes from other subglacial environments. Researchers have already discovered microbial life in isolated lakes trapped beneath the Antarctic ice. These microbes were found in waters thousands of meters below the surface, living in complete darkness. They survive by using chemical reactions, not sunlight. Some of these organisms appear to have metabolic pathways similar to those found in deep-sea vents. This suggests that extreme, isolated environments can support life given the right chemical conditions. Another clue comes from studies of ice cores. When scientists drill deep into polar ice and extract cylindrical samples, they sometimes find microbial cells trapped in the ancient layers. Many of these microbes are still alive despite being frozen for long periods. They survive in a dormant state, reviving once warmed. If microbes can survive inside the ice itself, it becomes reasonable to assume that some could survive in the liquid water beneath the ice, where conditions are far more stable. The possibility of life raises questions about what form it might take. If life exists in the hidden rivers, it is likely microbial. Large organisms require more energy than such an isolated environment can provide. Microbes, on the other hand, are resilient. They can survive in extreme pressure, extreme cold, low nutrient levels, and complete darkness. They can adjust their metabolic rates to match available energy sources. They can form biofilms on rocks, sediments, or the underside of the ice above them. They can float freely in the water or cling to particles drifting along the riverbed. Microbes living beneath the ice might not resemble familiar bacteria. They could have adaptations shaped by long-term isolation. Their membranes might be structured to withstand pressure. Their enzymes might function at temperatures close to freezing. Their metabolism might be slower than anything observed on the surface. They might form communities that depend on each other's waste products, creating cycles that persist with minimal external input. Some might use iron as an energy source. Others might rely on nitrogen cycles or sulfur cycles. Still others might use organic molecules left behind by ancient ecosystems, buried beneath the ice sheet long before it formed. If such life exists, it would offer clues about how life can function in extreme environments elsewhere in the solar system. Places like Jupiter's moon, Europa, or Saturn's moon Enceladus have icy surfaces with liquid water beneath. The conditions in the hidden rivers beneath Antarctica may be similar in terms of pressure, darkness, and reliance on chemical energy. Studying Earth's subglacial environments could provide insight into how extraterrestrial life might exist, what it might rely on, and how it might adapt. However, discovering life in the hidden rivers is as challenging as reaching the rivers themselves. As discussed earlier, drilling into these rivers risks contamination. If a drilling system introduces microbes from the surface into the subglacial environment, those microbes could outcompete any native organisms, permanently altering the ecosystem. This contamination would not only harm any native life, but also compromise scientific findings. If microbes are found, researchers must be certain they originated in the subglacial system, not from the drill system. Ensuring sterility is extremely difficult because surface microbes cling to equipment, hoses, water droplets, and even to the air inside the borehole. Another complication is that microbial life might not be evenly distributed. It could exist in concentrated patches where the chemical conditions are favourable. It might form layers along the bedrock. It might gather in sediments, clinging to particles in dense clusters. It might live primarily near geothermal hotspots, where warm water meets mineral-rich rock. If life is sparse or localised, a probe entering a subglacial river might pass by without detecting anything. This possibility means that even if life exists, finding it requires careful planning and perhaps multiple attempts. Scientists must also consider the risk of disturbing microbial communities that are adapted to extremely stable conditions. Introducing oxygen, light, or other unexpected stimuli could stress or kill these organisms. Even slight warming could disrupt their metabolic processes. The microbes might be so finely tuned to their environment that any sudden change could be harmful. This is why some researchers argue that if life is found in subglacial rivers or lakes, it might need to be studied in situ rather than removed for analysis. But studying life inside such a difficult environment adds another layer of complexity to an already complex problem. Chemical traces of life might exist even if living organisms are rare. These traces could include organic molecules, metabolic byproducts, or isotopic signatures suggesting biological activity. Some of these indicators might persist in the water or in the sediments beneath it. Detecting these chemical signatures would provide strong evidence for life even if the organisms themselves remain difficult to collect. However, interpreting these signals requires extreme caution. Chemical markers that look biological may also arise through geological processes. Researchers must distinguish between biological and non-biological sources with certainty before drawing conclusions. If life exists in these environments, some of it may have survived from ancient ecosystems that existed before the ice sheet formed. During periods in Earth's geological past, Antarctica and other polar regions experienced warmer climates. Rivers flowed on the surface, lakes filled broad basins, plants and microscopic organisms lived freely. When the climate cooled and ice advanced, some of that water, and possibly some organisms, may have become trapped beneath the growing ice. Over time, these trapped communities may have adapted to the new environment, becoming specialised for life in darkness and extreme pressure. Studying such organisms could reveal how ecosystems transform over long periods in response to environmental change. Another possibility is that life beneath the ice did not originate from ancient surface organisms but developed independently within the subglacial environment. Life forms could have evolved from microbes carried downward in meltwater, gradually adapting to the dark and cold. Others might have come from deep underground, carried upward by pressures inside the rock or by geothermal fluids emerging through fractures. These organisms might have merged or interacted with those descending from the surface, forming unique communities shaped by multiple origins. The complexity of these potential histories adds depth to the scientific interest in exploring the hidden rivers. Even without direct life detection, the environment itself might hold hints. Biofilms could leave traces on rocks. Sediment layers might contain structures formed by microbial activity, similar to stromatolites found in shallow marine environments. Minerals might form patterns influenced by biological processes. Such evidence could remain intact for long periods in the stable subglacial environment, but these traces would be delicate and easily disturbed by drilling equipment. Because of this fragility, scientists must design instruments carefully. They must detect microbial signatures without disrupting sediments. They must measure chemical gradients without altering them. They must avoid heating the environment or introducing oxygen that could change biological activity. Instruments must collect samples in sealed systems that prevent contamination both ways. The complexity of these requirements makes the search for life challenging, even when tools reach the water successfully. The potential discovery of life also raises questions about how it survives. What energy sources does it use? How does it reproduce in such cold conditions? How does it maintain cellular function at temperatures near freezing? Does it interact with minerals in the bedrock? Does it rely on slow-moving water currents to bring nutrients? Answers to these questions would expand our understanding of life's resilience and adaptability. They would show how ecosystems can form in conditions far different from the ones humans experience. The presence of life beneath the ice could also influence the stability of the hidden rivers. Microbial communities might help break down minerals, altering the chemical composition of the water. They might produce gases that accumulate in sediments. They might influence how sediments bind or release water. These interactions could shape the long-term behavior of the subglacial system. Life would not simply exist in the environment. It would interact with it, influence it, and change it gradually over time. The possibility of life also makes the ethical considerations stronger. Disturbing these environments could harm ecosystems that have survived in isolation for ages. Introducing contaminants could erase unique evolutionary histories. Researchers must balance the desire for knowledge with the responsibility to protect fragile environments. This responsibility echoes across many fields of science, but becomes particularly weighty when dealing with ecosystems that may hold the oldest and most isolated life forms on Earth. As the story continues, it becomes clear that the hidden rivers beneath the ice are not just a physical mystery, but a biological one as well. Understanding what lives there, or what might live there, requires a combination of geology, chemistry, biology, and engineering working together. And as we move forward, the next step involves looking beyond life itself and toward the broader implications these hidden rivers have for the future, how they influence the stability of the ice sheet, how they respond to changes in climate, and what they mean for the shifting world above. When you think about something hidden deep beneath the ice, it's easy to imagine it as separate from everyday life, tucked into a world far removed from anything people experience. The hidden rivers beneath the polar ice sheets feel distant in that way, sealed under kilometers of frozen mass, far away from cities, far away from warm air, far away from anything familiar. It's tempting to assume that what happens there has no real effect on daily life anywhere else. But the truth is that these hidden rivers play a role in shaping large-scale changes that eventually reach coastlines, weather systems, and communities across the planet. They are not isolated in the way they appear. They are part of a larger network of processes that influence the world's future. The first and clearest connection involves sea level. When most people hear about melting ice contributing to sea level rise, they picture icebergs breaking off glaciers or the surface layers of ice sheets melting in warm weather. But the water flowing beneath the ice influences how fast the ice above moves toward the ocean. If the hidden rivers increase in volume, they can lubricate the base of the ice, reducing friction between the ice sheet and the bedrock. This reduction in friction allows the ice to slide more quickly, feeding glaciers that carry ice from the interior toward the coast. Even a slight increase in the speed of these glaciers can add a significant amount of ice to the ocean over time. This process doesn't rely on visible melting at the surface. It can happen even when surface temperatures remain cold. The hidden rivers form their own system independent of seasonal conditions above. Their flow patterns depend on the pressure of the ice, the geothermal heat rising from below, and the structure of the bedrock. If climate change increases surface melting, and more water reaches the base through cracks and crevasses, the hidden rivers may swell. This added water can accelerate basal sliding, making glacier movement more sensitive to changes happening far away from the interior. The relationship between basal water and ice movement is complex, but it is central to understanding how the ice sheets will respond to warming conditions. Another factor involves how the hidden rivers influence the stability of the ice shelves around the edges of Antarctica. These ice shelves act as barriers, holding back the flow of glaciers behind them. If the ice shelves weaken or collapse, the glaciers flow faster, accelerating ice loss to the ocean. Hidden rivers flow beneath some of these glaciers before they reach the coast. As this water moves toward the ocean, it can alter the grounding line, the point where the glacier stops resting on bedrock and begins floating on seawater. If the grounding line retreats inland, it can destabilize the glacier, allowing it to flow more rapidly. Basal melting affects the grounding line because water can erode sediments, weaken the ice-bed interface, and alter pressure balances. In some places, this melting makes the ice less firmly anchored to the bedrock. Over time, the grounding line might retreat inland across sloping terrain. If that slope leads downward into deeper basins, the retreat can accelerate, causing further instability. These changes are not always sudden, but they can contribute to long-term shifts that influence how much ice enters the ocean. The hidden rivers also shape how ice responds to warming oceans. Warm ocean water can flow beneath ice shelves, melting them from below. But the rate and pattern of this melting depend partly on how fresh water from the hidden rivers enters the ocean cavity beneath the shelf. Fresh water is less dense than seawater. When it pours into the cavity from the base of the glacier, it rises, creating circulation patterns that can draw warm seawater upward toward the underside of the ice shelf. This process can increase melting, weaken the shelf, and contribute to fracturing. The interaction between fresh water from the hidden rivers and warmer ocean currents forms a feedback loop that affects the rate of ice loss. These connections illustrate why understanding the hidden rivers is so important for predicting sea level rise. Sea level projections depend on knowing how fast the glaciers will move, how strongly the ice shelves will hold, and how the grounding lines will respond to warming conditions. Without accurate knowledge of the hidden rivers and their influence, these projections remain uncertain. Researchers want to reduce this uncertainty not only for scientific understanding, but also for planning coastal infrastructure, preparing for future climate impacts, and advising communities at risk of flooding. Beyond sea level, the hidden rivers may influence broader climate systems through interactions with ocean circulation. As fresh water enters the ocean from melting ice sheets, it changes the density and salinity of the surrounding water. These changes can alter ocean currents, particularly in regions near Antarctica, where deep water formation occurs. Deep water formation is a key part of the global ocean conveyor belt, a system that redistributes heat across the planet. If freshwater input increases substantially, it can weaken or shift the circulation patterns, affecting weather, temperature, and precipitation far across the globe. Although the hidden rivers themselves do not carry large volumes of water compared to the total ice sheet, their influence on glacier movement makes them indirectly important for understanding how much fresh water will enter the ocean in the future. Their role is subtle but essential. They shape the pathways through which ice moves and melts. They influence how quickly ice transitions from land-based to floating. They contribute to the early stages of processes that eventually feed the ocean. Another aspect of these rivers that matters for our future involves the stability of the ice sheet itself. Ice sheets are not rigid blocks of frozen mass. They respond to changes in temperature, pressure, snowfall, and structural support. Hidden rivers can weaken certain areas by creating regions where the ice loses traction. They can carve pathways beneath the ice that alter stress distributions. They can create pockets of water that shift the weight of the ice sheet unevenly. These changes influence how cracks form, how crevasses propagate, and where ice flows more easily. In some regions, the hidden rivers drain subglacial lakes that fill slowly over time. When these lakes drain, the surface of the ice can drop by several meters. These surface depressions change how snow accumulates. They alter how ice flows into surrounding regions. They affect the stress patterns that determine whether an ice shelf fractures or remains stable. Understanding the timing and location of these drainage events helps researchers anticipate long-term changes in the structure of the ice sheet. As climate warms, the potential for increased surface melting becomes a critical factor. In some regions of Antarctica and Greenland, meltwater has begun to form ponds at the surface. These ponds can drive fractures downward through the ice, forming pathways that allow more water to reach the base. If enough meltwater reaches the hidden rivers, it can change their volume, speed, and pressure. These changes may create new flow paths, shift drainage basins, and increase lubrication. The consequences of this downward flow extend beyond the immediate area. They influence glacier speed, ice shelf stability, and regional hydrology. The hidden rivers could see increased activity in the coming decades, as surface meltwater reaches deeper layers more frequently. These rivers also matter for our future because they offer clues about past climate. Sediments carried by the rivers record the history of bedrock erosion, ice movement, and chemical interactions. If scientists can retrieve these sediments without contamination, they can study how the ice sheet changed during past warm periods. They can learn how the hidden rivers evolved in response to ancient climate shifts. These insights could help predict how the ice sheet will respond to future warming. The sediments may contain traces of ancient ecosystems, minerals formed under specific conditions, or chemical signatures linked to past temperature cycles. In addition to ice sheet stability and sea level rise, the hidden rivers hold relevance for understanding groundwater systems in cold regions. Beneath the ice sheet, these rivers interact with underlying sediments and rock in ways similar to groundwater systems beneath the surface in temperate regions. They create flow paths, transport minerals, and influence erosion. Understanding these interactions could improve models for groundwater flow in cold climates, helping communities manage water resources as temperatures change. The hidden rivers also carry implications for understanding the limits of where life can exist on Earth. If life is found within these rivers, even at a microbial level, it expands the known boundaries of habitable environments. It suggests that life can persist in places isolated from sunlight, sustained by chemical energy and stabilized by pressure. This has implications for astrobiology and the search for life beyond Earth. It informs the design of future missions to icy moons, directing researchers to consider environments where water exists in contact with rock beneath thick layers of ice. The hidden rivers beneath the ice sheet become a kind of natural laboratory for understanding how life might function elsewhere. Another important factor involves permafrost and greenhouse gases. In some regions beneath the ice, organic material from ancient ecosystems may remain preserved in sediments. If these sediments warm or experience change due to shifting water pathways, they could release gases such as methane or carbon dioxide. Although the amount of gas stored beneath the ice sheet remains uncertain, understanding the chemistry of the hidden rivers could help determine how stable these deposits are. Changes in subglacial water flow could influence the release of gases that contribute to global warming. The hidden rivers also influence how scientific exploration evolves. Technologies being developed to study these environments may later be used in other extreme environments, both on Earth and elsewhere. New drilling techniques, sterilization methods, and autonomous probes built for subglacial exploration could become tools for studying underground aquifers, deep ocean environments, or extraterrestrial oceans. The challenges overcome in reaching these rivers drive innovation in fields such as robotics, engineering, and environmental science. The hidden rivers have implications for resource management as well. While the idea of extracting resources from beneath the ice sheets is not something considered seriously today, understanding the geology and hydrology beneath the ice could influence decisions about land use, protected areas, and long-term planning. The rivers flow across regions that contain valuable minerals locked in ancient bedrock. Even if these rocks remain untouched, understanding their structure informs broader geological knowledge that supports resource analysis in other regions. Additionally, the hidden rivers affect how scientists and policymakers think about the boundaries of ecosystems. Traditionally, ecosystems are defined by visible features such as forests, oceans, and lakes. But the hidden rivers suggest that vast unseen ecosystems may exist beneath the surface, influencing processes that reach far beyond their immediate surroundings. This expands the concept of what an ecosystem can be and encourages a broader approach to conservation and environmental management. As climate change accelerates, the importance of monitoring these rivers becomes more urgent. Remote sensing tools, computational models, and field missions will all play a role in tracking how the drainage system beneath the ice responds to increasing temperatures. Scientists hope to predict changes in glacier speed, ground-in-line migration, and ice shelf stability more accurately. Understanding the hidden rivers becomes essential for forecasting future climate impacts. Even though the hidden rivers flow far beneath the surface, their presence influences the future of coastlines, weather patterns, scientific exploration, and environmental policy. They shape the story of Earth's changing climate. They reveal how water behaves under extreme pressure. They offer insights into the resilience of the life and the fragility of isolated environments. And they remind us that the world's most significant processes often occur in places we cannot see directly. As this narrative continues, the final step draws everything together by returning to the quiet world beneath the ice and reflecting on how this hidden environment connects to the broader picture, linking the deep past, the shifting present, and a future shaped by forces that move slowly, steadily, and almost invisibly beneath our feet. When you spend enough time thinking about the hidden rivers beneath the ice, something begins to shift in how the whole story feels. At first, the entire idea seems like a technical challenge, a set of engineering puzzles or scientific mysteries. Then it starts to expand into questions about pressure, ancient water, microbial life, and climate systems that stretch far beyond the frozen edges of the world. But eventually, after moving through all of that, your attention comes back to something quieter. It settles into the simple fact that these rivers continue to flow in their darkness, surrounded by ice, moving without urgency, unnoticed by the surface world for most of human history. Their presence is so steady, so uninterrupted, that it becomes almost comforting to imagine them doing exactly what they've done for ages, no matter what happens above. Thinking about them in this way brings a sense of perspective. The world on the surface changes constantly. The seasons shift, cities grow, storms come and go, and people move through their lives surrounded by noise, light, and motion. But beneath the polar ice sheet, none of that reaches the water. The rivers move according to pressure and rock and ancient pathways carved slowly over geological time. Their flow does not hurry because nothing in that environment forces it to. They follow gradients measured in millimeters over kilometers. They respond to slow changes in the weight of the ice above them. Their world has its own rhythm, shaped by a kind of patience that the surface rarely allows. When researchers study these rivers, they use instruments and models and radar systems to understand processes that unfold far below what anyone can see. Those tools are essential, but every piece of information that comes back carries a reminder that the hidden rivers are part of a world that moves on timescales far beyond what humans typically consider. Even a single drainage event, where a subglacial lake empties into a river network, can take place over months or years. The ice responds slowly, the river adapts, the drainage system rebalances, and everything continues forward in a steady, measured progression. Imagining this movement gives you a sense of how different these environments are from anything familiar. The water slips between layers of ice and rock, under pressure so great that it prevents freezing, even at temperatures colder than anything naturally found in most places on the surface. The sediments beneath the ice shift gradually as water flows over them. The minerals dissolve at a pace too slow to observe directly. Microbes, if they exist there, operate on energy budgets so small that their metabolic cycles may take days or weeks to complete what surface organisms achieve in seconds. Thinking about all of this encourages a kind of quiet reflection. It's almost impossible not to slow down a bit, even mentally, because the environment you're imagining will not move any faster no matter how quickly you think about it. The rivers beneath the ice do not respond to urgency. They don't accelerate when interest rises or slow down when attention fades. They continue at the pace set by physics, pressure, and time, and then you start to realize that the hidden rivers have been doing exactly that since long before the first humans walked the Earth. They have existed through entire cycles of ice sheet advance and retreat. They have persisted as continents drifted and mountains rose. They have continued flowing in some form through climate periods much warmer and much colder than today. Even when the ice sheets vanished during earlier interglacial periods, water would have followed similar paths across the bedrock, carrying sediments and minerals along routes shaped by forces older than human memory. Layering that understanding onto the present-day picture adds another dimension. The hidden rivers aren't just features of the ice sheets, they are reminders of how much of the world escapes everyday perception. They offer a glimpse of processes that keep shaping the planet whether people notice them or not. Scientists can measure them, model them, and learn from them, but the rivers do not depend on observation to exist or continue. They will keep flowing long after this moment in history passes, adapting slowly as the weight of the ice shifts, as the climate changes, or as the bedrock erodes. The thought of that ongoing movement creates a kind of quiet connection between the surface world and the deep environment beneath the ice. Even though the two places could hardly be more different, they influence each other in ways that are subtle and steady. The glaciers that move toward the ocean respond to the presence of water beneath them. The oceans that rise and fall with global climate cycles are influenced by how quickly that ice moves. The rivers beneath the ice respond to the weight of the glaciers above them. Everything ties together, even when the connections remain invisible. If you imagine yourself standing at the edge of the polar plateau, where the sky above is clear enough that stars look sharp and cold, you might picture those rivers moving far beneath your feet. The ice stretches in every direction, smooth in some places and fractured in others. The wind moves across the surface. Snowdrifts pile and scatter. The air is so still that even the smallest sounds feel loud in comparison. But under all of that silence, water continues to travel across the base of the ice sheet. It does not rush. It does not carve dramatic paths like surface rivers do. It moves steadily, pressing against the underside of the ice, guided by gradients too small to notice without careful measurement. Standing there, you'd see nothing that hints at the activity below, yet everything would depend on it. The ice would rest on the water in some places and cling to the bedrock in others. The movement of the ice would be shaped by where the water flows and where it does not. The weight pressing downward would create pressure that governs the temperature of the water. The cold temperatures above would seal the rivers away in permanent darkness. The world under the ice would remain hidden, but its influence would be felt. These quiet connections are part of what makes the hidden rivers so compelling. They remind you that understanding the planet requires looking beyond what's obvious. It requires exploring conditions far removed from everyday experience. It means thinking about cold temperatures, high pressures, and long stretches of time. The rivers beneath the ice are not dramatic in the usual sense. They don't form waterfalls or floodplains. They don't sparkle in sunlight or support forests. But they play a role in shaping the world in steady, persistent ways. If you follow that idea further, it becomes clear that learning about these rivers isn't only about science or prediction. It's also about noticing how small processes become meaningful when they're part of something larger. The flow of water beneath the ice is gentle, almost invisible in its effect, but when multiplied across thousands of kilometers and millions of years, it helps determine how ice sheets move and how coastlines change. This steady influence shows how gradual forces can shape the planet more profoundly than sudden dramatic events. There's something calming about that perspective. It suggests that the world doesn't always change through noise or chaos. Sometimes it changes through slow adjustments and persistent effort. The rivers beneath the ice offer an example of that. Their movement is continuous, subtle, and entirely unhurried, yet they participate in processes that extend across the entire planet, connecting polar regions to distant coastlines and influencing patterns that touch every part of the globe. In thinking about this, you might imagine how researchers feel when they stand near a drill site or fly over the ice sheet using radar instruments. They know the complexity beneath them. They know the questions that still need answering. But they also understand that the rivers will keep flowing whether or not those answers come quickly. This creates a sense of patience in the work, a recognition that understanding takes time, just as the rivers take their time carving paths through the ice. Even the idea of exploring these rivers requires patience. The challenges discussed earlier, drilling through thick ice, avoiding contamination, designing machines for extreme cold, interpreting signals that reflect from deep beneath the surface, all of these tasks take years of preparation. Teams spend seasons planning, testing, revising, and adapting. They learn from each setback, they refine their methods, and they return, again and again, to try to reach an environment that remains hidden not because it's distant, but because it sits behind layers that resist easy entry. In a way, this patient approach mirrors the rivers themselves. The hidden rivers do not rush, and neither can the people who study them. Both move according to conditions they cannot control entirely. Both respond to pressure, one literally, the other figuratively. Both continue forward despite obstacles. The connection isn't symbolic. It's simply a reflection of how the environment sets the pace for understanding. As you imagine all of this, there's a quiet sense of scale that begins to form. The ice above spans an entire continent. The water beneath moves through channels shaped by the bedrock. The stars above stretch across a sky untouched by city lights. Thinking about all these layers at once creates a kind of stillness. It places human concerns next to geological time, environmental stability, and slow-moving rivers of water locked beneath ice thicker than the tallest mountains. The contrast isn't meant to diminish anything happening on the surface. It simply places it within a broader landscape that has existed for so long and continues to move at its own pace. The more you picture that, the easier it becomes to stay with the story a little longer. You can imagine the quiet of the polar night. You can imagine the cold air. You can imagine the stillness that stretches in every direction. Beneath that stillness, the hidden rivers continue to flow, following their pathways through darkness. Their movement is not dramatic, but it never stops. They carry minerals, sediments, and perhaps even life with them. They support processes that influence the future, even if their world remains unseen. Spending time with that thought leads to another one. The hidden rivers aren't just part of a remote environment. They are part of the planet you live on. Their presence contributes to how coastlines will look in the coming centuries. Their flow patterns shape how glaciers respond to warming. Their chemistry might hold clues to Earth's history. Their ecosystems, if they exist, remind us that life adapts in ways that are not always obvious. Their existence is one more example of how much the planet holds beneath its surface. And when you place all of that beneath a sky filled with distant stars, the scale becomes even clearer. The rivers flow in a world without sunlight, yet they share the same planet as the people looking up at the night sky. They exist under layers that filter out all the sounds of the surface. They move through a landscape so cold and pressured that it might seem incapable of supporting anything. But they continue anyway, carrying their quiet story forward. As the narrative settles here, the hidden rivers remain exactly where they've always been, moving slowly beneath the polar ice, shaped by forces older than memory. They do not end. They continue into the next moment and the next, flowing through darkness that asks nothing from them, except that they follow the paths set by pressure, rock, and time, and everything above them continues as well. The ice shifts, the snow falls, the stars shine in the clear polar sky, and the world unfolds according to its own steady rhythm, just as it always has.